welcoming you again on the third day of this workshop. For this, I request Dr. Bipro Dhar sir to please begin the session.
All right, so good morning. Oh, it was off. Okay, now good.
Yes.
Okay, good morning, everyone. So, what happened to rest of the class? Okay, I think people still gonna join, but we are gonna get started because today we have to finish at least 3 topics. So last 2 days we primarily focused on like wastewater treatment. So today we are gonna actually move more towards like solid waste or organic waste management, and we are gonna also cover 2 different bioprocesses called anaerobic digestion and composting. Okay, so what is waste? So waste, garbage or trash, this is something like everyday items that we use, okay, and we throw them away. Okay, it can include a wide variety of components, okay, starting from food scraps, product packaging, grass clippings, furniture, clothing, cans, bottles, papers, appliances, different actually household hazardous materials like paint, batteries, okay, so even some electronic items. So solid waste, it's actually very heterogeneous collection of different types of waste, right? And solid waste in municipalities, solid waste can be generated from different sources, okay. So most of the time we focus on residential solid waste, okay, but solid waste can also be generated from school, hospitals and businesses, okay. And with growing population, okay, and urbanization and improving of our lifestyle, we are actually making more waste. And I was actually looking at some statistics, and due to rapid urbanization, economic growth, actually India is right now among one of the top 10 waste generating countries in the world. And another reason is actually the number of population, right? So this is actually another factor why India is within top 20. So as I said, solid waste can be generated from residential sources like household, apartment buildings, but at the same time solid waste can be generated from industrial sources like different types of manufacturing, fabrication industry, chemical plant, sometimes different commercial sources like store, hotels, shopping malls, restaurants, and sometimes institutional. It can be produced from school, hospital, university, government center, prison. So from when waste is generated from industrial, commercial and institutional waste, we kind of combine them together and we call them ICI waste, okay. So industrial, commercial and institutional. And solid waste can also be generated from construction and demolition, okay, projects, okay. So if you have any large construction project going on, that can actually significantly contribute to solid waste generation. And sometimes also municipal services can also produce solid waste. So for example, landscaping, water and wastewater treatment plants. So for example, we were learning wastewater treatment process, and one of the thing we learned that activated sludge process produce significant amount of sludge. So sludge is a kind of solid waste as well. It's considered as a solid waste. So so not necessarily municipal solid waste, or sometimes we use the term called MSW, so municipal solid waste. Not necessarily the majority part gonna come from residential sources. Sometimes as I mentioned, like if you have any large construction project going on in your city, like demolition and construction waste can also be a significant factor, okay, or significant portion of your waste. And but if we look into residential, a major portion of residential solid waste is actually organic, and you can have different types of organic component in there, starting from food waste, paper, cardboard, plastic, okay, one of the most problematic, like waste that we have, textile, yard waste, okay, wood, like in countries like India you might have yard waste throughout the year, but in Canada, like we have very short summer, maybe 6 months summer and 6 months winter. So for during winter we don't do any gardening. So mainly yard waste is generated actually during summer, and that kind of can be a problem, because that means like that characteristics of waste during summer and winter months, it might be significantly different, right? So anyway, so inorganic waste you can have glass bottles, ferrous metals, okay, aluminum cans, okay, and then some other item we considered as ash, okay. So those items cannot be, or ash or inert material, those items cannot be actually recycled, or like cannot be transformed into some other value-added product. So we kind of consider them as ash. But most of the time, like in most of the countries, majority of the organic waste is actually food waste and paper, okay. More than 50% in most cases is food waste and paper. So two major component, food waste and paper. And solid waste generation rate actually can be impacted by many factors, and some key factors are our lifestyle and activities and socio-economic condition, okay. For example, one thing you can consider, like when we were kind of raised mostly in our childhood in 90s, like early 90s, and at that time online shopping was not a practice, right? But nowadays I am not sure what about India. So how is online shopping? It's very popular here, right? And you order, like you don't go to restaurant, you order food using app, right? So that means, and everything, when you buy some product online, everything comes with some packages, right? So there are a lot of actually packaging materials like paper, plastic, that actually kind of increase. So if you see last 15 years, like trend in online shopping increased, at the same time like packaging material, plastic, paper, those actually component in solid waste actually significantly increased as well. And at the same time, socio-economic condition, this is another important factor. So for example, if if your income is high, you are going to actually buy more stuff, right? That means more stuff means more consumption, we are going to produce more waste, okay. So socio-economic condition is considered as one of the major factor in solid waste generation. And this is actually a graph from per capita waste generation rate versus human development index. Human development index is kind of an indicator, okay, like this is actually tool developed by United Nations to measure like social and economic development condition of different countries. So higher actually human development index means your like social and economic condition is better, okay. So you can see here like we can see a very nice trend. In the x-axis we have human development index, which is the data was taken in 2007, and on the y-axis you have waste produced kilogram per capita per person. So per person how much waste that you generate, okay. So you can see here some countries in some cities in South Asia, and they selected 20 cities, okay, and some cities in South Asia like Delhi, India, Bengaluru, India, Nepal, Dhaka, Bangladesh, right? In you can see here their human development index. So those are actually like India, Bangladesh, they are more like considered as developing countries, right? So their human development index is typically lower than if you considered with some developed countries like US, Australia, and some European countries, right? So you can see a very nice trend here. So with Human Development Index, actually like waste generation rate per capita is increasing. So for example, some cities in South Asia, it's around 0.8 or 0.7, but in most of the cities in US and Australia, they are more around 1.5 or more than 1.5, right? So your social and economic condition, it's kind of, you know, very closely intertwined with how much waste that we generate, okay? And not necessarily, and just, you know, like right now and over the years, actually it's increased significantly. So for example, in Canada right now, average waste generation rate is around 2.5 kilogram per capita per day. So per person around, I think 2.5 kilogram waste that we generate, okay?
Same in US right now.
Yeah, same in also almost same in US as well.
Very old data, so
Yeah, but Canada, I think one of the thing is waste especially food waste generation rate is really high, and I don't see any number from you know, like some Middle Eastern countries, but I think, you know, it's gonna be high as well, especially food waste, okay? This is kind of like, you know, I was in Dubai last summer, okay, for a conference for a week, and I could see how much food waste is generated there, okay? So they don't have, if you go to restaurant, like everything is kind of big plate, okay, and you just eat a small portion and then rest is waste, which is kind of like, you know, very insane, like, you know, it's not acceptable. So not necessarily just the you know, not necessarily just the amount of waste, okay? At the same time, characteristics of waste can also be influenced by actually social and economic condition of a country. So for example, like, you know, here you can see some data from low income versus high income country. Well, one of the major similarities, you can see the both low and high income countries, organic waste, this is basically food waste, because plastic is also organic, right? Mainly food waste. In low income countries it's 53%, but in high income countries it's around 34%. But in both low and high income countries, organic waste represent the most significant portion of your waste. Major difference, but other stuff like metal, textile, glass, plastic, okay, you may not see a big difference, but big difference you are gonna see in paper, okay. So in low income countries you have 6% paper, but high income countries almost 25% paper, and it's kind of like, you know, there are many reasons, okay. So one thing I could say, like, you know, more online shopping, okay. So even like, you know, nowadays I saw many people, even you need a toilet paper, you order that in Amazon, you don't go to the shop, which is yeah. So and everything, like, you know, they have good packaging. Like one day I actually ordered a USB drive, okay, very simple thing, and they had actually 3 different boxes, okay. So first it came with some, you know, boxes with the product, then another 2 boxes, some actually plastic wrapping, you know, like those you know, bubble wrap, okay, to make sure that it's not damaged during shipping. So you can see even a small thing, actually when you buy from online, it comes with a significant amount of waste, right? And why you should care about waste management? Because improper waste management create a lot of issues, okay. So for example, like, you know, if we, like, you know, or do open dumping for plastic bags, like, you know, one of the major challenging you know, major challenge in solid waste management, it can actually pollute water bodies with different types of organic and inorganic compound and pollutants, okay. You can have flooding because it can actually block the you know, like water network, okay, block the drainage system. At the same time, sometimes we see we kind of feel that, okay, instead of open dumping, if you send those waste material into landfill, maybe it's good, but actually it's not, because even in landfill, some, or if you, especially if you send some organic material like food waste in landfill, over the time they are going to degrade by microbes, okay. And microbes gonna actually generate methane. Okay, methane, like anaerobic digestion process, and methane we know that it's more dangerous greenhouse gas compared to carbon dioxide, right? So so waste management is a very critical, okay, for make sure we can actually protect our environment and public health. And even for landfill, actually in landfill produce a wastewater stream called leachate, okay, and leachate is actually one of the most dangerous wastewater on, or most hazardous wastewater on earth. You can have many different types of material, okay, that actually cannot be easily treated in biological process, okay. And 93% of waste in low income countries, they are actually dumped, like without any treatment, and 2% in high income countries. But let me tell you, like in some remote communities, even in countries like US or Canada, they have they don't have proper waste collection system, okay, or proper waste management system, and their situation, I can tell you, like almost same as some low income countries. If you go to like Asia or Africa, okay, so the picture is almost the same. So even high income countries, not necessarily everyone getting the same type of waste management services, okay. So India generate our statistics from India. So India, I'm not sure like which year data, I forgot to put that, but more or less it's over 62 million tons of waste per year, okay, and only 43 million ton of waste is collected, but still actually majority of waste is actually discarded without any treatment in waste yard, and out of that 62 million, only 12 million, okay, so only very small portion is actually kind of processed appropriately, okay. So waste management is it's a big problem, okay, and it's a big problem right now, and with the growing population, that problem is actually becoming even more intense over the years. And waste management include prevention, recycling, processing, disposal program, okay. So we have to actually collect the waste, process it, okay, and then like if we can recover something, we should recover or recycle, and then rest we should dispose safely to make sure that we are not damaging the environment, okay. So selection and application of suitable methods. So what kind of method that we should use? Actually there it's very critical, okay, to minimize the waste generation and maximize the reuse, recycling and material recovery. And sometimes actually like we generate waste, okay, and we don't know actually kind of some like small changes in our behavior can make a big difference in waste generation. So that's why like I'm not sure what's happening here, but many countries actually or many municipalities across North America, they spend a significant amount of budget to educate people, okay, so to educate people how we can actually minimize the waste, or how we can actually properly separate different types of waste to make sure that okay, like it can be processed easily, okay. So and we should also focus on energy recovery and dispose all the remaining waste in the landfill. So if we cannot recover or recycle anything, the only option gonna be landfill. So we cannot completely get rid of landfill, but we can minimize like what portion of waste is going to the landfill. And in waste management, this is something actually very popular these days, something called waste management hierarchy, okay. So you can see here, so our first objective in waste management should be reduce. So we should try to minimize the amount of waste that we generate, okay, every day. So if we can reuse something, we should try to reuse, okay. So use the materials repeatedly. So one of the thing like with in modern days, like disposable things are very popular, right? If you have an event, instead of using some ceramic plate or something, you go with disposable, right? It's very easy to use, you just use and dump, you don't need to clean it, right? So this is something, so we should try to promote, okay. We should actually reusing stuff. So if we can reuse something, we should try to reuse them and reduce the amount of waste that we generate. Recycle. So if we can recycle something, especially paper, okay, cardboard, plastic, sometimes it's not very easy to recycle, okay, but still we should try to actually focus on turning waste into new product. Recovery. So sometimes some stuff cannot be recycled. So for example, food waste you cannot recycle, right, but food waste can be a valuable resource to actually produce different value added product like compost or biogas, right. So sometimes if we can recover any bioproduct, we should try to recover them, and at the same time, you know, like if there are any residuals that we cannot either recycle or reuse or recover any resources, it should go to the landfill. But our most preferred, okay, option should be reduce, reuse and recycle. So we call it actually 3R approach. So this is something actually widely used these days, like, you know, something called 3R, zero waste, many other terms actually used in waste management industry to promote this 3R. So and that 3R, reduce, reuse and recycle, can lead us to a significant cost saving in our waste management, okay. And again, the disposal would be the least preferred, but obviously we cannot completely get rid of the landfill. So key elements in municipal solid waste management system is collection, transfer and transport. So collecting waste, okay, and then you actually take them to the facilities properly, okay. That's actually a big challenge, because sometimes actually collection, especially some low income countries, there is no appropriate collection system, okay. So there is no appropriate collection system which lead to actually open dumping, okay. So you cannot collect everything, every waste that is actually generated. So collection, transfer and transport to the waste management facility, this is a key element. And then second key element is processing. So if there are some recyclable material, you should try to recycle them, okay. If there is any organics that we cannot recycle, we should try to see if we can use some bioprocess and convert them into some value added product. And then finally we should separate the any kind of residual or inorganic items or any items that we cannot reuse or recycle. We should actually dispose them in landfill. So collection system may vary in different countries, okay. Residential collection system is usually in you know, most of the developed countries, they are actually provided by municipalities, sometimes by private companies, but in most cases municipality provide, like, you know, waste and wastewater services, okay. You have to either pay the fee or sometimes it can be included in your property tax. But in less developed countries or low income countries, they do not have formal waste collection system, okay. So how is the collection system here in Allahabad? Is there any like service that is provided by the municipality? Okay. So how everything is mixed together, like, you know, food, no segregation. So okay, yeah. So maybe you never know, maybe after 10 or 15 years later, okay, you have to segregate your waste, okay, and then it's going to be collected separately, because now countries are actually becoming more concerned about the impact of. Okay. So after collecting, it's segregated in the facility, okay. But so, and how about the fees? You pay fees or it's actually included in the property tax? But they are not getting money from so that money has to come from somewhere, huh?
Property tax all depends on the state government plans.
Okay. So
in India, mostly municipalities are not profit making. Few municipalities are profit making, such as Allahabad, Surat. Allahabad is having a very good model. They are more profit.
Okay.
Because they actually calculate the property tax according
Okay, okay.
This kind of calculation.
Okay, okay. So like in Canada, in our city, we pay about $600 per year for just for collection. So more or less you can see per person is producing in Canada close to 1 ton of solid waste per year, right? So if you have 3 person at home, you are actually paying close to $200, okay, $200 per person, so or per ton of waste. But typically tipping fee for solid waste is around from $100 to $120. So that means $100 or $120 is for collection, and then $100 or $120 is for processing the waste. Okay. And typically 2 types of collection track, okay, you can have in for solid waste collection. So one is called haul collection system. So haul collection system is actually container used for storage. So container used for storage of waste or collection of waste is actually taken to the disposal site. Okay. So for example, this kind of collection system is very popular for collecting waste from high waste generation areas. So for example, like if you have a big construction project going on, right? So typically there are big, those waste container where everything is dumped, and then the whole container is actually taken to the facility, okay, either landfill site or solid waste management facility. But for household waste collection, another system is popular, which is called stationary waste collection system, okay, especially for single family household. So stationary waste collection system, how it works? So container used for storage. So there, every house they have kind of small container, and on the garbage day, we call it garbage day. For some community it could be Friday, some community it could be Monday. Okay, so you take your container to the curb, and then it's actually collected by the truck. Okay, so some cities they have like a truck with mechanical arm, so they don't have any worker, just the driver. So they are actually collecting the waste because municipality provided those waste container. They are same size, right? So it's easy to collect for them. So container used for storage remain at the point of generation, okay, and the collection truck it collect from one location to another location until the truck is full with waste, and when truck is full, they take all the garbage to the disposal site or processing facility. So even 15 or 20 years ago, okay, waste management facility most of the time actually refer to landfill site. Okay, even like the interesting thing is, if you see the course syllabus for solid waste management, okay, back in early 2000, you are gonna see, not necessarily here in US or Canadian universities, most of the time solid waste management course was mostly focusing on landfill design. Okay, so solid waste means landfill design, nothing else. But nowadays actually it significantly changed, okay, because now industry trend is quite different. So they want to get rid of landfill. Okay, even our province of Alberta, they had a mandate, like they want to make landfill free Alberta. So landfill free doesn't mean that, okay, we completely get rid of landfill, but we want to divert at least 90% so waste from landfill. Okay, so very small portion we want to send to landfill site. And actually in Canada, the number of landfill sites are very high compared to some European countries. Okay, and what was the reason? Because Canada is a very big country. Okay, we are the actually second largest country in the world, but if you see the population, okay, I'm not sure, like we have 41 million people. Maybe I don't know, maybe in I know in Dhaka there are more than 20 million people, right? So how about Delhi? What is the population in Delhi?
Should be more than 10 million at least.
It should be more than, yeah. So that's why we had actually lot of open space. So it was actually, they did not actually, so we are not limited by footprint. So landfill was the cheapest option to build. But if you go to European countries, they actually are very aggressive in solid waste management. They adopted many actually advanced technologies because they were limited by footprint, right? They don't have actually a lot of space.
But here I have a question. Actually, I have seen this argument many times that they don't have landfills. But I have also read somewhere that they send their waste, which could be landfill, to some underdeveloping countries or developing countries.
Yes, there were some actually report that especially some stuff, if they cannot incinerate, okay. So in Europe, incineration was the very popular practice. So you basically burn everything, you get 90% of volume, 5% of volume reduction, and only small portion of inert material like ash is left. But some stuff like, let's say, electronic waste, you cannot do anything. So they were mainly shipped to some African countries, okay, and actually their e-waste was actually became a big problem for them, okay. So yes, you are correct that some of the items were actually shipped to other countries, and actually I'm going to get into that. Actually, like industry now facing big challenges these days. So anyway, let's go back to our current topic. So previously, waste management facility used to be only landfill, but modern waste management facility, we have many different unit operation, okay, or many different facilities. So one is called material recovery facility, or MRF. So what is MRF? MRF is basically the facility where different recyclable items are sorted, okay. So for example, paper, plastic, cardboard, okay. So everything is sorted, okay, and then baled, and then it's actually shipped to the manufacturing industry for turning into new products, okay. Composting facility is basically for processing food and yard waste, okay, or any kind of organic waste that is biodegradable. Anaerobic digestion facility, but composting facility is more popular because composting facility is composting process is cheaper compared to anaerobic digestion, okay. But still anaerobic digestion is I believe quite popular in India. I was actually looking into some statistics, and in India there are close to 4 million anaerobic digester, okay, and but out of that 4 million, actually 3 million are household. So that means many villages, okay, they have small those biogas digester, that is actually, so they use their household organic waste and produce biogas to actually for cooking, right. Some thermal processing facility like incineration is actually very popular in Europe because they were actually kind of landlocked, right. They did not have enough land space to build landfill site. So thermal processing is actually very popular, and some site actually also include, not some site, actually most of the site also include landfill. So for example, in our the city where I live, we have material recovery facility, composting facility, anaerobic digestion facility. We had thermal processing facility, but that was not incineration, that was gasification. But unfortunately, that facility was closed last year, okay, because gasification is kind of like little bit advanced process compared to incineration. So they were actually, I'm not sure what was the challenges exactly, but that facility was closed. But we used to have thermal processing facility, and at the same time we also had a landfill in the province where I actually so here you call state, okay, in our in Canada we call provinces, okay. So in our province we have about 300 landfill site, okay, and every year provincial government spend about $150 million to manage them, okay. So material recovery facility, okay, basically it's for recovery of recyclable items. In some here, as you mentioned, that it's not segregated, so everything is mixed together, okay, and then it's actually taken to the facility and separated. But in some high income countries or developed countries, they are actually collected separately. So you have to put your garbage in one bag, okay, if any recyclable items in a separate bag, like in blue bag or blue bin, and food waste is actually collected separately, food or yard waste. Okay. So there are 3 different streams that is actually coming from each household. So what we have in recyclable or items, so we can have paper, cardboard, plastic, glass, metals and aluminum. And aluminum, like aluminum cans, like it could be from beer, soft drinks, and this is kind of like it's highly recommended that we recycle this kind of items. So for example, metal mining actually kind of like has a very large carbon footprint, right? So if we can actually recycle some of the metals, actually it's kind of based on life cycle assessment, it was showing that it can significantly reduce the emission. Okay. And material recovery facility include both manual and mechanical separation. Okay. Why manual separation? Although like these days yesterday we talked about machine learning, AI, right, artificial intelligence, but still like some stuff can be done by human more effectively, because machine may not identify some of the items, right? So if you have some most of the time if you go to any facility, okay, regardless of how advanced it is, okay, most of the time the first step is manual sorting or manual separation of items, because like worker, they can easily identify what kind of material, if it go to the downstream unit processes, then what kind of item can create problem. So for example, sometimes let's say in your kitchen blender it's suddenly stopped working, but you think, okay, what, there it can be recycled, and you put it in the blue bin. Okay, you put it with good intention, but if it actually go to the facility and if it actually go to some unit process, actually it can damage the facility or damage the equipment. So that means actually they have to shut down and actually repair, right? So it can be actually big economic challenge for the facility. So that's why still manual sorting, it's a actually very critical process in material recovery facility. And at the same time you can have different types of mechanical processes like disc screen, glass breaker, cyclone, magnet, eddy current and so on. Okay, and those units separate the item based on the physical characteristics of the items. Okay, for example, based on size, density, magnetic properties. So if you have large items and small items, and if you use a screen, you can easily separate large items from small items, right? If you have some ferrous iron, you can easily use magnet, right, and separate them from the stream. If you have some non-ferrous item like aluminum can, you can use something called eddy current. If you have plastic and glass bottle, plastic are lighter material, right, and glass bottles, they are heavy, you can actually use something called air classifier. Okay, so you can like provide high velocity of air, okay, and that can actually separate heavy items from lighter items. There is something called optical sorter. Optical sorter is kind of advanced unit or equipment that can actually sort plastic based on their type and color. Okay, because plastic is the most problematic thing, because there could be many different types of plastic, right? So it could be PET, it could be HDPE, right? So PET is much more transparent. Okay, for example, our water bottle, it's PET, but some stuff could be like non-transparent or heavy plastic like HDPE. So it's kind of like very difficult to actually sort them based on their type and color and everything, right? And another challenge, actually, like I was telling, so most of the recyclable item that is actually generated in developed countries, previously they were shipped to China. 90%, okay, was shipped to China before until 2018. Okay, and why? Because most of the manufacturing industries, they were in China, India. And why? Labor cost, low labor cost. You are going to see most of the thing, like even Apple iPhone is actually like it's actually produced in China, right? So the same thing for recyclable material. More than 90% of the recyclable material that was actually produced in developed countries, they were actually shipped to China. But now China over last 15 or 20 years, their economy was booming. Okay, so now they have economic growth, they have population, and they are actually generating significant amount of waste. So they don't need waste from other countries, right? But now countries like Canada, US, they did not build manufacturing industry that much, right? Because like the cost is high, so shipping was cheaper for them, because they could just generate revenue from by selling those items to some manufacturing industries in China. But now in 2016 or 17, China was actually informing most of the municipalities in North America that, okay, you know what, from January 1st 2018, okay, we are not going to take your waste if it's contaminated. So if you are actually shipping us paper and if you have some plastic in there, we are going to actually ship you back. Okay, we cannot take this kind of item. So your item must be 99.9% pure. Okay, so without any contamination. But like most of the municipalities, they thought, okay, you know what, like they are just scaring us, more like tariff these days. So they thought, okay, you know what, it's not going to happen and we can still do that. But now actually China 2018 January 1st, they were very strict. They said, okay, they ship them back. And many municipalities in North America, they actually stored their belt recyclable item for a couple of months. They could not ship it anywhere, and they were actually forced to ship them. They were actually forced to actually send those material to landfill. So you actually separate the item, you put them in blue bag, you thought it's going to be recycled, but actually it was going to the landfill. Okay, for I think it especially 2018 and 19 was very challenging for most of the municipalities. But meanwhile, what happened, some other countries like in Africa, okay, countries in Asia like Thailand, India, they were actually building new manufacturing industries. They wanted to actually take advantage of this market, because now price of those items decrease because demand is less, right? So they were actually so nowadays most of the recyclable material from Canada is I think coming to Thailand, India and some other Asian countries. Okay. So yeah, so yes, we know that some item can be recycled, but still it's not that easy. Okay. So composting is mainly used for biodegradable organic waste into carbon dioxide, water and heat is generated in the process. And so this is more like aerobic process. Okay. So aerobic process, we learned that actually microbes, they use oxygen, right, and produce carbon dioxide and water. So composting process is similar to that. And at the end of the process, we produce a stabilized solid which is called compost. And compost, so in the process, during the biodegradation process, actually carbon is degraded, right, but nutrient and phosphorus like nitrogen and phosphorus, they are still there at the end of the process. And we know that nitrogen and phosphorus, they are very important for plant growth, right, they are like a fertilizer. So compost was actually compost is actually very popular slow release fertilizer. Okay. Another bioprocess that we can use for organic and biodegradable waste is anaerobic digestion. Anaerobic digestion is done by anaerobic microbes, so they do not need any oxygen. Okay. And in absence of oxygen, they degrade the organic compound and produce carbon dioxide and methane gas. And we know that methane, and typically biogas contain 40 to 70% methane and 30 to 50% carbon dioxide. And there is lot of application of anaerobic digestion. Anaerobic digestion can treat, digestion process can treat a wide variety of organic waste, not necessarily just or food waste or yard waste. We can use manure, we can use wastewater sludge, different types of food waste, and biogas can be actually used to generate heat and electricity, which is kind of very popular. Okay, we call it CHP process, combined heat and power generation unit. but nowadays people are trying to get more value added product from biogas. So one of the thing is upgrading biogas to renewable natural gas, or we call it RNG. Okay, so renewable natural gas, if you can remove the carbon dioxide and other impurities, it's going to be close to 95 to 97% methane, so which is close to natural gas. So you can actually directly inject that in the grid. Methane can also be actually used to produce bioplastic. Okay, but the yield is quite low. Okay, yield is quite low, and lot of other bioproduct can be actually produced from anaerobic digestion process these days. But heat and electricity and RNG, they are kind of most common product, okay, or most common application, because for other application like bioplastic, yield is low, so it's not economically still feasible yet. Thermal processing, there could be three types of thermal processing. Okay, incineration is the most common one. Okay, incineration process can give us heat, and we can also produce actually electricity from incineration. There are some other advanced thermal processing technologies available, like pyrolysis and gasification. So pyrolysis process give you oil, bio oil, okay, or sometimes we call it pyrolysis oil, which is very close to crude oil, petroleum crude oil. Okay, but maybe energy content gonna be little lower compared to, or energy content can be lower than petroleum crude, and there are some upgrading challenges, but still you can produce bio oil using pyrolysis process. And the process also use something solid product, bioproduct called biochar. Okay, possibly you heard about biochar. I think in the first day we talked a little bit about biochar. There are many different environmental application of biochar. You can use it for water treatment, right? And some people also use that biochar for soil amendment as well. Gasification process use actually produce something called syngas. Okay, synthetic gas is it's a mix of carbon monoxide and hydrogen. Okay, so carbon monoxide and hydrogen, and syngas can be further converted into some biofuel like ethanol or methanol. Okay, and what is the application of ethanol or methanol? It can be blended with your petroleum oil. Okay, it can be like in Canada we have a mandate that actually most of the provinces, they want at least 5 to 10% of our regular gasoline is actually mixed with 5 to 10% ethanol or methanol. Okay, so incineration, pyrolysis, gasification process, they are all of them, they are actually operated at high temperature. Okay, but the major difference between incineration, pyrolysis and gasification is the amount of oxygen that you provide in the process. So incineration process, it's actually it's a combustion process. Okay, so you combust everything, so that means the you need to provide oxygen for combustion. Okay, so excess amount of air is actually provided in the process. And pyrolysis process, this is actually done without any oxygen. Okay, and gasification process, you provide partial amount of oxygen. So that's why when you don't have enough oxygen, carbon is kind of combined with oxygen, but not enough oxygen for complete combustion. So instead of carbon dioxide, you end up with carbon monoxide. Okay, and hydrogen gas.
So among these three processes, which one do you feel is having less environmental impact?
It's hard to tell. Okay, I think pyrolysis and gasification, they are still in pilot scale. Okay, pilot scale. Incineration is kind of widely implemented. Okay, it's kind of like already established.
A lot of air pollutants like oxygens.
Yeah, dioxin and others, but you can actually, we know how to control them. Yes, it's kind of like you have to have some facilities to deal with that, but pyrolysis and gasification, they are still, I think, lab or pilot scale. Actually, first gasification facility was in our city, Edmonton. So first demonstration was in Edmonton, but as I said, the facility was closed last year. So that means still there are some challenges. If the facility was running properly, there was no point that they closed it, right? So pyrolysis and gasification, still it's not a market proof right now. Okay, but I'm not sure, like maybe I'm pretty sure if you
I have seen many plants based on
pyrolysis,
pyrolysis. They use plastics.
plastic, okay, a large scale or like large scale. So yeah, pyrolysis, because biochar production is kind of very popular these days. Yeah, very popular these days. So pyrolysis, it's not very challenging, but gasification, the problem is you are producing syngas and you have to further convert syngas to some product, right? So you need actually two facilities, not just gasification. You need like some sort of catalytic conversion process that can actually convert syngas to some biofuel. But I am pretty sure if you search online, you are going to see some systematic studies on life cycle assessment of different processes. Okay. So landfilling is the last option. Okay, landfilling is the last option. If you cannot actually reuse anything or recycle anything, or cannot recover any value-added resources from our waste, we have to send them to landfill. And landfill actually engineered facility for safe disposal of waste. So it's not just dig and dump your waste. Okay, you have to make sure that they are safely disposed. Okay, and it's not actually affecting your, it's not contaminating your groundwater, or not actually creating any air pollution or anything. Okay. One of the major challenge with the landfill is landfill produce actually significant amount of leachate. Okay, so and leachate, as I was telling, it's one of the most hazardous wastewater on earth. Okay, so it's not actually possible to treat leachate using just simple, it's not like municipal wastewater. You cannot just use, treat it without with just a simple biological process. Okay, you need some advanced physicochemical process to deal with landfill leachate. Okay, so and even let's say some landfill sites are closed. So let's say you have a landfill site, it's completely full, you are not dumping waste, but maybe 50 or 60 years you have to still deal with the leachate. Okay, and over time even leachate production gonna be higher. It's even gonna be more concentrated with different types of pollutants, right? So it become even more challenge, like like over time. So that was kind of like an overview of solid waste management industry, currently what's going on and what kind of processes that we have to deal with our waste. But for rest of today's lecture, gonna be focusing on two processes, because this course is on environmental bioprocesses, right? So we are going to cover two topics, composting and anaerobic digestion process. So why don't we take 5 minutes break, okay, and then we will continue with our next topic, composting. Okay, thank you. Yeah, sure. Yeah. What is time now? 10:30. Okay. So 11:15 we are going to take another break for 20 minutes. Okay. So we are going to start our second topic today. Second topic on biological waste treatment processes, number 1, and under number 1 we are going to cover composting. Okay. So we already learned that actually composting, it's an aerobic bioprocess where microbes, okay, and some other large organisms actually can degrade or transform the organic content in your solid organic waste like food waste, yard waste, and convert them into a soil like material called compost. Okay. And biodegradable material, so not necessarily just microorganisms, okay, you can utilize for composting. Sometimes some vermicomposting, there is like something called vermicomposting. So even larger organisms like earthworms can also be used for composting process. And as you can see here from this picture, here is organic waste, and after conversion to compost, it's like more like soil type material, and it's very rich in nutrient. Okay, so it can serve as a slow release fertilizer. Okay, slow release fertilizer, and it can actually also reduce the use of your chemical fertilizer, right? And another benefit of using compost is the water holding capacity of like compost is very high. So that means if you use compost for your agriculture, you are going to need less watering. Okay, so it can also save your cost for irrigation. So the fundamental of composting, so it mostly done by microorganisms, but other organisms can be used, as I mentioned. And carbon like material is actually converted to carbon dioxide, water, humic and product, which is kind of a compost. Okay, and the process also actually produce heat. Okay, so that means like aerobic activated sludge process, composting process, we also need to provide air in the process, because those microbes, they need oxygen as electron acceptor. Okay, you remember that, that's good. Okay, so yeah, so we need actually oxygen in the process, and the process is going to produce carbon dioxide, water, and release heat, but at the same time some odorous compound can also be generated like ammonia, sulfide. And for like any biological process, okay, there are some optimum range of operating or environmental parameters for composting, and one critical factor in composting is carbon to nitrogen ratio in the feedstock. Okay, so optimum carbon to nitrogen ratio for composting process is 30:1. Okay, but well, if it's 25:1 or 35:1, still it's okay. But if you are actually using, if your primary feedstock is, let's say, 10:1, then it's not a like good idea to use that item as a sole feedstock for your composting process. So to carbon to nitrogen ratio, it's a big factor in composting or any biological process. Okay, because microbes, they produce carbon more quickly, right? Even if you remember, like we are writing a chemical formula C5H7O2N, right? They need more carbon and less amount of nitrogen. Composting process, you also need to make sure that you have enough moisture, okay, because microbes, they also need water in the process. So 50 to 60% moisture content you have to maintain. Oxygen content 10 to 15%, okay, because you need oxygen as electron acceptor there. pH, like they are mostly bacteria, okay, so 6 to 8 neutral pH. And particle size, it's very important. You have to make sure that particle size is between 0.5 to 2 inch, okay. And sometimes it's kind of problematic because solid waste is kind of very heterogeneous, right? So you can have a wide range of different sizes, particle sizes, but sometimes pre-processing may be required. Okay, but for composting, pre-processing of feedstock is not a common practice. But if you have large particle size, that means your composting time gonna be more. Okay, you have to actually keep them for longer time to composting process to be completed. And steps involved in composting are actually inspecting the feedstock. So first of all, if you receive a feedstock for your composting, first you have to inspect the feedstock and you have to actually remove any undesired items. So let's say if you have any plastic bag, some broken glass or any sharp material, okay, you have to actually remove them, you have to take them out, otherwise they are going to be in your final product and the quality of compost not going to be good, right? And even sharp material, if it's there, it's also not for safe. Okay, and then after inspection and removing undesired items, you have to actually prepare the feedstock. So what is preparation? We just mentioned that carbon to nitrogen ratio has to be like within some optimum range, like 30:1, right? So now let's say your facility received a feedstock, but carbon to nitrogen ratio is not within a proper range, then you have to actually find another complementary feedstock that you can mix together, okay, and reach some optimum carbon to nitrogen ratio. Okay, and then after your feedstock is ready, you can start your main process, which is called active composting and curing. Okay, that's kind of like the longest part or the key part of your composting, and there are 3 different phases in composting. Okay, so first is, it's more like, you know, we talked about microbial growth curve yesterday, right? So composting, it's also a batch process. Okay, so you have almost the same thing, lag phase and exponential phase, stationary phase, and you know the decay phase in composting we call it curing phase. Okay, so lag phase, active phase and curing phase, and then finally after composting process is done, typically they are sell it to the market. You have to actually final compost after processing is done, you have to screen them, okay, before you actually kind of bag and sell it to the market. So inspection of feedstock include removing of unacceptable or non-compostable item that can actually impact the finished quality of the finished compost product quality. Okay, and inspection and preparation may include different steps. So one thing I mentioned, like mixing different types of feedstock to achieve some desired carbon to nitrogen ratio. Another thing could be particle size. Okay, so particle size, if it's too large, then that means your composting process is going to be very long, and you don't want that, especially when you are limited by footprint, right? In that case, maybe you may go with some pre-treatment process to actually kind of maybe grinding to reduce the particle size, because microbes like they cannot actually break down large particle, right? So you need sometimes need some sort of pre-treatment. Okay, and so carbon to nitrogen ratio, it's an indicator of relative amount of nutrients and carbon. Okay, so low carbon to nitrogen ratio means high nitrogen content, and high carbon to nitrogen ratio means higher proportion of carbon, and both are actually not good. We know that actually like microbes, they have more they kind of more quickly or faster metabolism for carbon. Okay, but still you need nitrogen as a nutrient source. Okay, and so that means to make sure that we can achieve a desired carbon to nitrogen ratio, and as I was mentioning, we don't need exactly 30:1. If it's 25:1, 35:1, it's still fine within some good range. So this is kind of like step by step. First we need to identify the primary feedstock for our composting, and then we have to know the desired properties. Okay, so we have to characterize if carbon to nitrogen ratio not within a range. We have to identify a secondary feedstock, we have to blend them. Okay, but we have to know, okay, how much of the primary feedstock is mixed with how much of our secondary feedstock, right? So we need to know that. So first of all, we have to characterize carbon to nitrogen ratio for our primary feedstock. We have to characterize carbon to nitrogen ratio for our secondary feedstock. Okay. So we need to know how to calculate proper mixing ratio. So let's see an example. Okay, how we can do that. So, but before that, a typical carbon to nitrogen ratio in different types of organic waste that is actually generated from our household. Food waste 15:1. Okay. Green grass 10:1. Leaves 55:1. Wood chips 200:1. Newsprint 400:1. Cardboard almost 600:1. Right. None of them are actually 30:1. So that means if you use a single feedstock, it's not going to work. Sometimes actually compost, we can do it actually in our backyard, right? So I'm not sure. Someone you do composting at home? Huh? Okay. So I also actually do composting. I used to do composting, okay, during summer. But typically what happened, like, mainly for vegetable scraps, okay. So we kind of put it in some bucket, okay, with some inoculum, and then leave it. Typically, if I do it this year, I use it in the following year, okay, because it takes really long time, because I don't actually maintain any carbon to nitrogen ratio or anything, right? So it's kind of like more natural composting. So that's why it takes almost a year to get the compost. But think about facility; they cannot keep your garbage for a year, right? The composting process to be done. So if you do in centralized facility, you have to make sure that everything within optimum range. You can finish the process within few weeks, and you can move on with the next batch, right? So this is a simple equation that we can actually use to calculate how much of primary feedstock to be mixed with how much of secondary feedstock, okay, to actually achieve some sort of target carbon to nitrogen ratio, okay. So you can see here dry weight of carbon in feedstock 1. So number 1 is my primary feedstock, and dry weight of carbon in feedstock 2 is my carbon in my secondary feedstock, okay. And you can see here in this equation, so we need dry weight of carbon and dry weight of nitrogen for both. And why dry weight? Okay, because we have to consider dry weight because our organic waste contain a significant amount of moisture, right? So that's why we consider dry weight. And here in this equation, S is the mixing ratio. So the amount of feedstock needed per kilogram of primary feedstock. Okay, so that's the equation. So let's see an example. Blending of waste to achieve an optimum carbon to nitrogen ratio. So for a composting process, solid waste A with a carbon to nitrogen ratio of 40 is to be blended with solid waste B, and for solid waste B carbon to nitrogen ratio is 5. Okay, so we have primary feedstock which is carbon to nitrogen ratio 40, we have secondary feedstock very low carbon to nitrogen ratio 5. So now my equation is, and moisture content for A is 40%, moisture content for B is 60%, and nitrogen content is 0.2%, and nitrogen content for B is 1%. So I want to know if with 1 kilogram of A, okay, how much of B should be mixed, okay, to achieve carbon to nitrogen ratio of 25. Okay, so we are going to go back. So we can start with a basis of 1 kilogram. Okay, we can consider, okay, I have 1 kilogram of waste. Okay, so and I know that there is moisture there. So if I have 1 kilogram of waste, if there is 40% moisture in there, that means dry weight gonna be 60%. So if I have 1 kilogram of waste, 600 kilogram gonna be the dry weight, right? And out of the dry weight, I have 0.6, yeah, 0.2%. So 0.2% means 0.002, 0.2 divided by 100. So I have out of that 0.6 kilogram, I have 0.0012 kilogram of nitrogen.
It should be 0.02, right?
it was 0.2.
Yeah, it's okay.
Yeah. So now I know carbon to nitrogen ratio is 40, right? So if I 40 multiply by the amount of nitrogen, I can get the amount of carbon that I have, right? So for the second feedstock, we can do the same thing. For B, we know that moisture content is 60%. That means dry weight gonna be out of 1 kilogram, 400 gram gonna be the dry weight for B. And nitrogen content was about, I think, 1%. Okay, so that means multiply by 0.01, so 0.004 kilogram. Okay, and then carbon to nitrogen ratio is 5. So now I have both, you know, like in 1 kilogram how much carbon and how much nitrogen we have in both, you know, feedstock. We have the number. Okay, so now I am ready to use my equation. So I can actually plug those numbers there. So S is 0.2. So that means with 1 kilogram of feedstock A, I have to add 0.2 kilogram of feedstock B, and that gonna give me carbon to nitrogen ratio of 25. Okay, so that simple calculation actually can help you to estimate, okay, how actually we can actually mix different types of feedstock and make it ready for composting. And not necessarily just for composting. This concept can be used for other biological process like anaerobic digestion process, because carbon to nitrogen ratio is something important for any biological process. So you can actually use this same approach like for even for anaerobic digestion process. Okay, so that's why we covered this topic now in this composting chapter. So we are not going to talk about this again in anaerobic digestion, but you may need even for anaerobic digestion process, optimum carbon to nitrogen ratio is almost the same, 30:1. Okay, because they are heterotrophic biomass in both process.
What is the significance of S?
Huh?
How the S is defined?
Sorry.
How is the value of S is defined?
So 0.2 kilogram. So we have to, if I have 1 kilogram of feedstock A, okay, so before composting process, to reach carbon to nitrogen ratio of 25, I have to add 0.2 kilogram. So that means your total gonna be 1.2, right? And 1.2 you are gonna have carbon to nitrogen ratio of 25. Make sense? Okay. Okay. So another part of preparation could be adding bulking agent. So what is bulking agent? Sometimes, you know, like so composting process need oxygen. Okay, and it's not like wastewater treatment plant that you are, you know, 24/7 you are actually supplying air in the process, right? So composting process typically we don't provide active air circulation. Sometimes what we do, we mix the feedstock, okay, and then we leave it for like a week, and then after a week, you know, we come back, we kind of, you know, turn them, okay. So it's not active like, you know, 24/7 aeration. So that's why, but sometimes, you know, like feedstock may be very compact and they are not going to be enough diffusion of air in the, you know, compost pile, right? So that's why some facilities they add some material called bulking agent. Okay, bulking agent can be straw or wood chips. Okay, so when you mix wood chips and straw with your feedstock, okay, they are typically not easily biodegradable, right? So wood chips is not going to be easily biodegradable. Like if you compare with food waste and wood chips, food waste is going to be degraded, but wood chips it needs really long time to degrade, right? So but when you add both kind of material, you can have like, you know, more pores, and actually air can easily diffuse in the compost pile. So that's why those materials are actually added as bulking agent. And bulking agent they have little to no decomposition, okay, and after the composting process is done, okay, you can simply screen them, okay, and reuse those bulking agent again for your next batch of composting. So that's how it looks like, you know, composting, and it can be reused after screening of final step. So now after you prepare your feedstock, you start the process, and then first step gonna be lag phase. Okay, first step gonna be lag phase, and lag phase is period of adoption of microbes, as we learned in yesterday in microbial growth curve. So microbes, they need some time to adapt with the feedstock first, okay, and then they are going to actually start to break down the organics slowly, okay, and microbes, they are going to start to grow, okay, because microbes, why they degrade, we know that actually they want to grow. It's a part of their growth process. So they are going to actually start utilizing different types of organic sugar, starch, cellulose, amino acid that is actually present in your feedstock, and they are going to start to grow. And so that means microbial activity going to increase, and at that time what you are going to see, if you remember one of the previous slide, so the process also generate heat. So you are going to see in the compost pile, temperature going to start to increase, okay. So one of the important monitoring parameter in composting process is temperature. So temperature is an indication that actually your composting process is running properly or not. So when you are going to see your temperature started to increase, that means the process started, your lag phase is ending and it's kind of reaching active phase. So active phase, you are going to see exponential increase in microbial activity, which going to be,
Is it log phase?
huh?
Is it log phase?
It's kind of log phase, but they call it active phase. Yeah. So it's like, you know, log and stationary, I would say. So log and stationary combined together, and we call it active phase. Different book, different, but again it's exponential or log phase plus stationary phase. So it's indicated by a increase in temperature, okay. So that temperature increase gonna continue until microbes, they have enough food, okay, they have enough food. So when you are gonna see temperature started to decrease, that means your curing phase started and your active phase kind of ended. So temperature is a monitoring parameter. But what if you see temperature starting and suddenly next day, instead of like, you know, gradually decrease in temperature, it's kind of sharply, maybe from 60 degrees Celsius, next day if you see 25 degrees Celsius, then there is something wrong, okay. There might be some sort of inhibition, okay, or maybe microbes, they don't have enough oxygen, so they kind of, you know, they are completely got inhibited. So there could be some sort of malfunction. So that's why temperature is in centralized facility. Maybe when you do it at home, you don't actually monitor temperature, but when you do it in the facility, you have to make sure that you monitor the temperature, because that's kind of like give you an idea what's going on in the process. So but at the same time, you have to make sure that temperature should not go above 70. If it goes above 70, then it's a problem. You are going to actually kill all the microorganism, right? It's mostly like you are sanitizing. So but again, a sudden drop in temperature during active phase is an indication that some sort of actually malfunction happened, okay, and you have to take immediate action, okay. One thing, you can go and check pH. If pH is acidic, okay, then that could be a problem. If you don't have enough oxygen in there, that could be another problem, okay. And the final step is curing phase. So curing phase means microbes, they do not have enough of organics, so they are kind of you know, their activity is declining over time. So you are going to see gradually temperature going to start to decrease, and curing phase can be you know, like it depends on the what kind of feedstock that you are dealing with. Curing phase, for some feedstock it can be very short, for some feedstock it could be very long, okay. And it depends on feedstock, it depends on what kind of process you are using, okay. Maybe you know, if kind of like, you know, mix the feedstock in more regular basis, the process is going to be faster, right. So this is a typical temperature profile in compost pile, okay. So typical temperature profile, you can see in the decomposition. So decomposition is basically lag and active phase. Okay, you are gonna see temperature starting from ambient temperature, it's kind of increase and go close to 60, and then it slowly started to decrease. So this part we call it maturation or curing, and this part we call decomposition, or different book they use different term, but decomposition is lag plus active phase, and maturation is basically curing phase. So when you do it in industrial scale, there are different options that you can use. Okay, there are different strategies that you can use. So and most of the centralized facility, they have 3 types of system that can use. So one is called aerobic static pile. Okay, so this is one process that you can use. Another process is windrow composting. So basically you have if you can do it outside, and you can actually pile the composting material in different windrows, okay, and leave it for some time. Some facility also use vessel type or bioreactor type composting process. And why is that? Because when you do it in vessel, it's easy to actually control some of the parameter, okay, and control and monitor some of the parameter is much easier when you do it in aerobic static pile or windrow composting. But again, the selection of the process depends on how much money you have, right? Everything, end of the day, it's about how much capital investment you need, okay, and land availability. So typically windrow composting, you need much more larger space, but if you go with vessel type, okay, you can build a vessel like a silo type, okay, so that means you need a small footprint, okay. So it depends on many other factor, but obviously windrow composting is the easy one, easy to actually control. When you go with vessel type, you need much more skilled people to operate this kind of facility. So windrow composting is the simple process, okay. So you basically compost, you can do the compost by piling solid waste into a long semicircle shaped piles. You can see here in this figure, okay. So you can have multiple those semicircle shaped piles where you can actually stack your waste, okay, and you don't have any activation, but maybe every weekly or every couple of weeks you have to come back and turn them, okay. So then you have enough oxygen in the compost pile. And piles are usually actually they aerated either manual or mechanical equipment, okay. In this kind of, if there is large facility, maybe you cannot do it mechanical, you need some you cannot do it manually, you might need some mechanical equipment to do that. And that's why you can see with between 2 piles you have some space, right. So if you have any mechanical equipment, you need some space to actually move them, right. So that's why you see there are some space between each windrows.
Sir, this is basically like people do in rice mill with rice.
Yeah.
Same technique.
Yeah. And this method can handle large quantities of diverse types of organic waste. But one of the major challenges, weather condition. Okay, if you have heavy rain, then everything gonna be washed away, right? So that's a problem. Cheap thing always come with lot of challenges, right? So it's kind of, you have to accept that. Another process is almost same, but instead of passive aeration or intermittent aeration, you can actually have a network of pipe, and then you actually kind of pile your waste or compost material on the that over that network of pipe, okay, and whenever needed you can run the pump, okay, or blower, and you can actually provide air in the process, okay. So that's kind of easier, you don't need to move any equipment around. And aerobics, vessel type of or bioreactor type composting process, okay, that is mostly used in some developed countries, okay. For example, in Canada we have 6 months winter, right. So that means actually we cannot do it outside most of the time. So, but even in winter, we cannot stop eating during winter, right? So, we have food waste generated throughout the year. So, what we would do? So, that is why sometimes actually some facilities they used vessel type or bioreactor type of composter. Okay. And actually, like previously we used to have a composting facility that could actually process 80,000 tons of solid waste every year, which was actually in our city, that was one of the largest in North America composting facility. But that facility was closed, and then now actually municipality is moving more towards anaerobic digestion process. Yeah, but still we do composting in summer months. They are actually done in outside, but other city. So there are two big cities in our province, Edmonton and Calgary. But Calgary right now they use this kind of process. So this method can also process actually large amount of waste. Okay, because you can have like silo type. You have like you can have some bioreactor with like tall bioreactor, like silo type design. So instead of like you can actually build them, or you can actually treat more waste, okay, with small footprint. And this kind of bioreactor type organic waste, bioreactor type system can handle any kind of waste. And why? Like you can use meat, animal manure, biosolid, food scraps. Sometimes when you do it outside, if you have, let's say, meat product or manure, they create odor. Okay, and if those facilities are near residential areas, people gonna complain. Okay, so that's actually major problem, because sometimes like typically in Canada, most of the waste management facility, they are typically far from residential areas. Okay, otherwise people gonna come and complain about odor. So odor is a major problem, but if you have bioreactor type, you can easily actually control the odor problem. So the process actually comes with, this kind of process comes with lot of control system and lot of sensors. Okay, but at the same time it's gonna be more expensive, as you can expect. Okay,
Is it feasible for hilly area, mountain?
Well, it depends. Like you can actually do it anywhere. You can build like there are drum, silo type, or concrete line trench. Okay, so you can build it anywhere. It doesn't matter. Like in hilly areas, you can build houses, right? So why you cannot build some facility like this?
Temperature doesn't have any effect.
Sorry.
Temperature, if it is beyond 0 degree minus.
Oh, at winter it might be problematic. Yes. In that case, you have to possibly like supply hot air in the process. Yeah, so that's why actually in our in Edmonton, the anaerobic digestion facility, it was actually large steel structure building. So they actually have everything inside the building, and building during winter months it's heated. So they used to maintain 37 degrees Celsius inside the building always. And air was always recirculated. There was a biofilter outside, so any air, okay, was continuously 24/7. It was recirculated between biofilter. So exhaust air was going to the biofilter, treated, and then you kind of bring it back. So yeah, like temperature could be a problem.
What is the maximum amount of volume it can have?
It depends. I think different design comes with different capacity. Okay.
What about the seeding? Is there any inoculation that
Inoculation, yes, yes. You have to actually, yeah, mixed. Yeah, you have to add some. Maybe you have to actually collect some inoculum from your first batch, like obviously before curing. Okay. And then use that as an inoculum for the second batch. So we have three options. We have windrow, we have aerobic static pile, we have reactor in vessel. And if we go from windrow to reactor vessel, the cost, operating skill, and process and emission control you have to invest more. So that process is going to be more expensive. But windrow, we need more space, but it's a cheaper option. So if you have open space, okay, and if weather is good, then possibly windrow composting is the most cheapest option that you can select, and it's most cost effective and most widely used process. And typically those for windrow composting, okay, they are actually organic material. They are kind of they are formed into long piles, okay, and they are typically semicircle shape, okay. They are in semicircle shape, may not be perfect semicircle, but for our engineering calculation we consider it's perfect semicircle, right? I cannot go and measure whether it's perfect or not, right? So for engineering calculation we consider it's perfect semicircle. So, and windrows are typically 1.5 to 3.5 meter high, okay, so you cannot go beyond that, and typically 3 to 6 meter wide, okay, and between two windrows you have to keep some space, 1 to 5 meter, to make sure that you can move your mechanical equipment for aeration, okay. So let's see an example. Calculate the total area and number of semicircle windrows required for composting, okay. Our total volume of waste to be composted is 50 meter cube per day. So let's say the facility is receiving 50 meter cube per day, and the composting time gonna be, total time gonna be close to 100 days, right? So for 100 days, whatever the waste is collected, we collect them in batch, and we actually gonna run some composting process in batch. And now we consider the length of the windrow is 25 meter, okay, and space around the perimeter. So this is something like, let me draw it on the board. So you have multiple windrows. So you have to keep some gap with two windrows, and you also need to keep some gap here on each side. This is called space around the perimeter. Okay, so we are saying that the length of the windrow is 25 meter. So this is 25 meter. And space around the perimeter is 3 meter. Okay, so we are saying every, here it's 3 meter, here it's 3 meter, here it's 3 meter, okay, 3 meter. And distance between two windrow is 4 meter. So between two windrows we have to keep 4 meter. So I want to estimate, okay, what is the total area that I need if I decide to go with windrow composting, okay, and how many semicircle windrows we can have, okay. And windrows we can go up to 8 meter diameter, okay. So now every day we are generating 30 meter cube of waste, okay. So in 100 days we are going to have 5000 meter cube. So now surface area of the windrow, so they are semicircle, and for circle it's pi r square, right. So semicircle pi r square divided by 2. So you have 25.13 meter square surface area. Now we know the length, which is 25 meter. So if I area multiply by 25 meter, I can get what would be the volume of each windrow, okay. So what is the total amount of waste or volume of waste we can have in each windrow, right. So 25.13 multiplied by 25, so each windrow we can have about 628 meter cube of waste, okay. So now my total waste is 5000. So if I divide 5000 by 628, we need about 7.96 windrows, but I cannot, we are not scientists, we are in engineering we kind of like to round numbers. So instead of 7.96 I will consider, okay, we are going to have 8 different windrows. Okay, so we are going to have 1, 2, 3, 4, 5, 6, 7, 8 windrows, and each side we have to keep space around the perimeter 3 meter. We have distance between each window 4 meter, and length is 25 meter, right? So now I can easily calculate the length. What would be the length? So space around the, so 25 meter, and on both sides 3 meter, 3 meter. So I have 25 plus 2 multiplied by 3, right? So 31 meter, my length gonna be 31 meter. But now what is the width? So width gonna be, you have diameter 8 and you have 8 windrows, right? So 8 multiplied by 8, 64. So 8 multiplied by 8, 64. We have gap between two windrows 4, and I have 8 windrows, so that means we have 7 gaps, right? So 7 multiplied by 4, okay, 7 multiplied by 4. Now on both sides I have 3 meter and 3 meter, okay. So 3 plus 3, so or 3 multiplied by 2 is 6. So 64, 28. Can I have 5 more minutes? Yes. Okay. So I have just one more example and then we'll take a break. Okay. So we have on both sides, so width gonna be 98 meters. So if I multiply 98 by 31, so this is gonna be my area. I'm gonna need about 3000 square meter of footprint if I want actually go with windrow composting. So another example, after this example we can go for tea break. Okay. So calculate the number of semicircle windrows and distance between two windrows required for composting. So here the diameter of the window is 3 meter. So height gonna be, because we consider it as perfect semicircle, 1.5 meter, and length is 15 meter. We want to know how many windrows we need and what should be the distance between two windrows if we have some limited space like 1245 meter square. Okay, and every day 14.6 meter cube waste is generated, and we assume that our composting process gonna take 50 days. So each batch gonna run for 50 days, and space around the perimeter is 2 meter, like previous example it was 3 meter. So now let's see. So first we have to estimate what is the total volume of waste that we are going to be dealing with. So 50 days multiplied by 14.6, so 730 meter cube. Now I can calculate the area of semicircle, which is pi r square by 2, so which is 3.53, and we know the length, which is 15 meter, and 15 meter here you can see. So volume of each window gonna be about 53 meters cube, and our total volume of waste is 730 meter cube. So we need about 13.78, or I can round that round up, I can make it 14. Okay, so we are going to need 14 windows. So now here we don't know, we want to estimate what should be the distance between two windows, right? So like previous example we knew what is the distance between two windows, but here we don't know. So first we can actually calculate length. So length gonna be 15 meter plus on both side you have 2 meter and 2 meter, right? So 15 plus 4, 19 meter is my length. But width I have 14, right? 14 windows. So 14 multiplied by 3, okay? 14 multiplied by 3, and distance between two windows I don't know, but I know I have 14 windows, right? That means I'm gonna have 13 gaps. Okay, I can consider, okay, you know what, the length gonna be x. Okay, so 13x, okay, and space around the perimeter on both sides going to be 2 meter and 2 meter. So 4, so 46 plus 13x. So we know the length, and for width we have this, okay, but we know the total area. So 46 plus 13x multiplied by 19, and my total area is 1245 meters square. This is my total area available. So I can easily solve this, and x is 1.5. So that means with this limited space I can only keep 1.5 meter of distance. Okay. Yeah. So here we are finishing the composting chapter.
In the previous example, you have already given the space.
Yeah, yeah.
So I assume that this is the ideal.
Actually, ideal is here.
The first problem.
Actually, here. So you have to keep 1 to 5 meter, and if you have 1 point, but if I have less than 1 meter, then it could be a like concern. Okay. Possibly if it's an engineering design class, we would go back, okay, and try to see whether we can actually increase the height, okay, and give more space in between. Okay. Yeah. Okay. So let's take 20 minutes break for your tea break, and then we'll continue with the next topic on anaerobic digestion. Thank you. So our next topic is anaerobic digestion. Okay. So so far I think we talked a lot about like aerobic processes, bioprocesses. We talked about activated sludge process and some other processes, and then this morning we also talked about composting. So the next one is anaerobic digestion process. So anaerobic digestion process, I think like already some of you are familiar with the process. It's a multi-step biochemical process where actually microbes, anaerobic microbes, so those microbes for their metabolism, they do not need any oxygen. Okay. So in absence of oxygen, they break down the organic compounds that you have in your organic waste, and they can produce methane. Okay. So carbon in organic waste is reduced to methane, and there are two types of microbes work together. So two types of anaerobic microbes, we call them bacteria. I think most of you are familiar, but another type of microbes also actually work in anaerobic digestion process. We call them archaea. So bacteria is basically they break down the organics, okay, and actually produce some simple compounds and hydrogen gas, and then in the final step archaea further convert them into methane gas. So not necessarily.
Archaea is umbrella name for methanogens.
Yeah. So for methanogen we call them archaea, not bacteria. Still, if you see some old books, maybe that is actually published in 1990s or before that, or even early 2000, you are going to see they call it methanogenic bacteria. Even still, I can see sometimes I get to review paper, okay, and I see people use methanogenic bacteria, which is not correct now. Okay. So previously they used to be actually bacteria and archaea, they have lot of similarities. Okay. They look almost the same size and shape. They also actually kind of grow by binary fission like bacteria.
Even the identification process is similar.
But the major difference in their cell wall. So for bacteria they have peptidoglycan, archaea they actually the cell wall is more on lipid. Okay. So they don't have peptidoglycan like bacteria, and some archaea they can actually grow in some extreme environment where actually bacteria cannot grow, like about 90 or even close to 100 degrees Celsius. Some archaea have been found they can grow. Okay. So let's come back to the anaerobic digestion. So in addition to organic waste like food waste or yard waste, we can actually use a wide variety of feedstock for anaerobic digestion process. So for example, we can use agricultural biomass, we can use manure, we can use sludge that is actually produced from wastewater treatment process. Anaerobic digestion process can also be used for wastewater treatment, but that wastewater needs to be actually high strength. Okay. So not like diluted wastewater we have in like domestic wastewater. Like if you remember from our previous lecture, COD. So what is the COD for domestic wastewater? What is the range? You remember? 400 to 500, right? But for anaerobic digestion process, you need at least few thousand milligram per liter of COD. Okay. So you can still use it for wastewater. So for example, like some countries, like some European countries, they have source separation of wastewater. So for example, the wastewater that is coming from toilet, that is actually kind of considered as black water, and that is actually treated in anaerobic process. But wastewater that is coming from other places in your home, for example from your kitchen sink, laundry, from your shower, typically you don't have high organic content, right? So sometimes they actually recycle that waste. So they use some physicochemical process and recycle that gray water for, let's say, gardening or some other stuff. Okay. So you can still use anaerobic treatment for wastewater, but it has to be concentrated. So anaerobic digestion process can give us biogas, which is mainly rich in methane. We can actually like combust them in combined heat and power generation unit and produce heat and electricity. Another option is we can upgrade the biogas to renewable natural gas by removing carbon dioxide and some other impurities like sulfide, and you can actually use is as an alternative to natural gas. Okay. Another evaluated resource that we can get is the digestate. So anaerobic digestion process can remove organics, mostly organics, but at the end of the process some organics still remain, okay, in the digestate, and lot of nutrients like nitrogen and phosphorus gonna be in the digestate. So that is actually a good biofertilizer for plants, but again you cannot directly apply them to the land, you have to meet certain criteria. Okay, different countries follows different criteria, but more or less most of the countries they adopted those criteria from US EPA, US Environmental Protection Agency. So if you have pathogen content under a certain limit, we call them class A, and we can actually use it anywhere. But if pathogen content is high, that is considered as class B, you have some limited application, you cannot actually apply it anywhere. So process fundamentals, it's a multi-step biochemical process. So that means there are multiple steps involved in the process, okay, and multiple types of microorganisms, they kind of work together, okay. So we call it synergy. So one metabolite produced by some microbes is utilized by another type of microbes, okay. So it's a very good synergy among different types of microbes, or syntrophic interaction, okay. So the process involved more or less like 4 steps: hydrolysis, acetogenesis, and then final step is methanogenesis. Some books you are gonna see they consider hydrolysis and they combine acidogenesis and acetogenesis together and call it fermentation, okay, and then the final step is methanogenesis. But again it's like if it comprehensive if you divide the different biochemical steps, you have 4 steps involved. So first the process start with hydrolysis, where actually complex organics like carbohydrate, lipid, protein. So if you consider any kind of organic like food waste, you mostly have carbohydrate, proteins and lipids, right? 3 types of organics. So in first step, some microbes they actually have enzymatic activity, they break down those complex organics to simple organics, low molecular weight simple organics. For example, carbohydrate can be hydrolyzed to sugar, protein can be hydrolyzed to amino acid, and fat can be hydrolyzed to fatty acid, okay. So then actually other fermentative bacteria, okay, so they do 2 type of process, acidogenesis and acetogenesis. They use those soluble organic molecule and then they produce something called more simple organic volatile fatty acid like propionate, acetate, butyrate, okay. So and then some other microbes further break down those volatile fatty acid to acetic acid. Acetic acid is actually also a type of volatile fatty acid, okay. So but let's say if you have in this process, if you have butyric acid or propionic acid, they are actually further break down into acetic acid, and the process also generate hydrogen and carbon dioxide, okay. So acetic acid, hydrogen and carbon dioxide, those 3 are the major precursor for methane production, okay. Then you have the final step where methanogenic archaea, they are not bacteria, they are archaea. So there are mainly 2 types of archaea. So one type of archaea, they use acetic acid and then convert acetic acid into methane plus carbon dioxide. So we call them acetoclastic methanogen, okay. Acetoclastic methanogen actually use acetate and produce methane and carbon dioxide. On the other hand, another type of archaea, we call them hydrogen trophic methanogen, okay, or hydrogen utilizing methanogen. What they do, they use hydrogen and carbon dioxide and combine them and produce methane. So that step doesn't produce any carbon dioxide, but this step actually produce some carbon dioxide, okay. And and most of the time anaerobic digestion process you have 40 to 70% methane and 30 to 50% carbon dioxide. So still a significant portion of carbon dioxide, and most of the time, like it has been found that actually acetoclastic methanogen, they are much more dominant in most of the digester. Okay, but it has been found that actually hydrogen trophic methanogen, they are more resilient. Okay, if you have some unfavorable metabolic condition, they can survive better than acetoclastic methanogen. So like composting process, there are some optimum process parameter for anaerobic digestion process as well. So for example, they prefer neutral pH 6.8 to 7.2. You need to provide enough alkalinity. Okay, you must have enough buffer in the system. Why? Because if we go back, the process actually produce volatile fatty acid or organic acid, right? So when you have organic acid, it is going to actually consume some of the buffer to neutralize, right? So you have to make sure that you have enough buffer in the system, otherwise pH gonna drop. And once pH drop, it doesn't matter, you adjust the pH back to neutral pH, it's not gonna work. Okay, it's kind of like some sort of irreversible process. So if acidification happen in your digester is gone, you have to restart. Okay, and alkalinity you need from 2000 to 5000 milligram per liter as calcium carbonate, and carbon to nitrogen ratio optimum is between 20 to 30, close to and here we can do the same thing. This morning we learned the concept how to actually estimate. Okay, different types of feedstock can be mixed together to achieve some desired carbon to nitrogen ratio. So we can apply the same concept here. Okay, as I mentioned. So those microbes also need nutrients. Under macronutrients they need nitrogen and phosphorus. Under micronutrients they need different types of metal like iron, because iron is needed to actually boost the enzymatic activity of microbes. Copper, zinc, nickel, but we don't need to add them. Typically we consider that in incoming waste or wastewater, whatever dissolved metal you have, possibly it's enough, or dissolved micronutrients you have, maybe it's enough for the microbes to grow. Toxicity, it's a major problem. So when you operate the anaerobic digestion process at higher organic loading rate, okay, then you could have different kind of problem. What different kind of problem? Let's go back here. So typically bacterial process, so the steps done by bacteria, they are faster process. Okay, but archaea, typically they are slow growing microbes. Okay, so that means your process for bacteria, it's going to, so their growth kinetics is faster than methanogen. So now you are running your reactor at high organic loading rate. Now bacteria, they are working very well, they are producing volatile fatty acid, okay, at very high rate, but your archaea, they are slow growing microbes. So they cannot cope up with the metabolism or rate growth kinetics of bacteria, right? So at some point what's going to happen, you are going to have volatile fatty acid accumulation in the system, right? They are producing at a higher rate, but methanogen, they cannot consume them at a higher rate, right? So some organic acid may be actually accumulate in the system. So now they are going to be acidification. So that's why process disturbance, it's a very common problem in anaerobic digestion, especially when you operate at higher organic loading rate. Like yesterday we learned about BOD loading, right? So Vs naught divided by V of the reactor, right? So sorry, Qs naught divided by V. So the same thing actually works for you. Have a, when you operate the digester at higher organic loading rate, you have more disturbance in the process. And sometimes process can also be inhibited by ammonia, process can be inhibited by sulfide. Okay, so especially for ammonia, let's say you have food waste, sometimes you can have very high protein content, right? So protein, when it's hydrolyzed, it releases significant amount of ammonia, and at high pH and temperature, ammonia can be mostly in the form of free ammonia gas, and free ammonia gas can actually kill the microbes. Okay, so you can have different types of toxicity by organic acid, ammonia, sulfide, and mixing sometimes actually it's so mixing, it's kind of like a very I would say it's a puzzle for researchers still. So we kind of believe that okay, high mixing means we have no mass transfer limitation, right? So process can be actually like you can very high mass transfer rate and process can work better, but that's not necessarily the case. Okay, so higher mixing can actually negatively affect sometimes the microbes. Actually we also did a study, it was done actually with one visiting student from IIT Kharagpur. Actually he worked with me for a year before COVID, and we did some study on mixing, and we found that actually like high mixing, so it's kind of like it can impact the microbial community. So you need some sort of moderate mixing or intermittent mixing. Maybe you mix it for like 15 or 20 minutes, okay, and then you leave it for 1 hour without any mixing, then you mix it again. So not necessarily high mixing can give you better performance. So sometimes for digestion process you also need to optimize the mixing intensity. Based on temperature, typically we have two types of anaerobic digestion process, mesophilic or thermophilic. So there is psychrophilic as well, but psychrophilic is not very common. Most of the time mesophilic at 37 degrees Celsius, it's a common industry practice, 35 or 37 degrees Celsius. So you can see here at different temperature, growth rate of anaerobic microbes is different, right? So at psychrophilic temperature growth rate is low, mesophilic it's moderate, thermophilic it's kind of good. But why thermophilic is not a common practice? Any thought?
Maintaining temperature requires much.
Huh?
Maintaining temperature is expensive.
Yes, that's one thing. Other reason? Sorry? Sorry, I could not understand. Okay, actually well, not necessarily there is inhibition. Okay, so what if I'm understanding you correctly, you are trying to say at high temperature it can be inhibited, but actually not, because it's growth rate. But yes, at some point it can be inhibited. And when? Because faster at high temperature means faster rate, and at high temperature when you have faster rate, you can have more imbalance between bacteria and archaea. Okay, so you can easily see like at high temperature bacteria, they are producing lot of volatile fatty acid, but methanogens still they cannot actually cope up with them. Okay, so you have more acidification problem at or process disturbance at thermophilic temperature. Okay, so that's why mesophilic temperature is the most common practice. But yes, high energy input is one thing, like obviously compared to 37 degrees Celsius or 35 degrees Celsius, at when you run your digester at 57 degrees Celsius, it is going to cost you more. Okay,
So mesophiles are responsible for production of VAP.
sorry, mesophiles. Well, both can actually produce, but the problem is so let's say
So to answer your question, what I am feeling that why we are not going for higher temperature, because mesophiles and thermophiles need to stay together.
well, when you run at thermophilic temperature, everything gonna be thermophile. At that time, actually, like let's say you start a digestion process using mesophilic inoculum, and you are running at thermophilic, then most of the time mesophilic they are gonna actually disappear from your system. Mostly it's gonna be thermophile. But the problem is not between mesophile or thermophile. The problem is about imbalance, and that imbalance gonna be even more intense at thermophilic temperature. Okay.
We can maintain the number of population of thermophiles at a temperature of mesophile, but if we opt for thermophile, it's very hard to manage the mesophile population.
Yes, we found that actually mesophilic, it's kind of they are much more resilient. Okay, if you let's say collect your inoculum from a digester that is actually operated at 35, and if you run them at 25 or 30 degrees Celsius, still it works good. But if you try to do some experiment with mesophilic inoculum and try to do some thermophilic experiment, it never actually work properly. So thermophilic, they are much more sensitive. Okay, so they are much more sensitive than mesophilic. Their growth rate is high, their decay is also very high. Okay, so they can grow very fast, they can also die very fast. So that's why actually mesophilic, okay, most widely used. So now they are depending on your type of the feedstock that you use for your digester, okay, especially the solid content, okay, there could be two types of anaerobic digestion. So if you are dealing with some wastewater sludge or high strength wastewater, it's mostly homogeneous, right, mostly water and very less amount of suspended solid, maybe 5% or 2%, right. So when we have very low solid content, especially less than 15%, we call it wet type anaerobic digestion. So wet anaerobic digestion. But when we are dealing with high solid content feedstock, so for example like food waste, yard waste, okay, so typically they have moisture content, let's say 60 or 70% and 20 to 30% solid, then the process is called dry or high solid anaerobic digestion. So there are many terms used for high solid anaerobic digestion. Some people use dry anaerobic digestion, some people use high solid anaerobic digestion, some people use another term solid state anaerobic digestion, okay. But I am okay with other terms, but I don't like the term dry anaerobic digestion. Dry means microbes, they cannot survive under dry condition, right, they need moisture, so it's not dry. I am okay with using high solid or solid state, but typically I use, because in Canada industry they mostly use the term high solid anaerobic digestion or HSAD, okay. So in this lecture we are going to learn little bit more focus on HSAD, because today we are kind of like, you know, I think last 2 days we got enough of wastewater, so we want to focus little bit more on solid waste side. So I am going to, rest of my lecture I am going to be mainly focusing on high solid anaerobic digestion. But before we jump into high solid anaerobic digestion, I want to talk little bit more what are the pros and cons of wet and high solid anaerobic digestion. By we can have a side by side comparison of both process. So you can see wet type anaerobic digestion, it's we need like, you know, low solid content feedstock like less than 15%. But we don't actually run it at 15%, it's mostly I would say 2 to 5% or can be 7%, okay, because
By volume or by mass, sir?
it's a, sorry,
As total solid 15% you are saying.
it's solid content, total solid,
By volume or by mass?
it's by volume. So milligram per liter, something like that. So if you have, let's say 2%, that means it's going to be 20,000 milligram per liter. Okay. So if you running at 5% solid, that means 50,000 milligram per liter total solid.
So all of them then they will be like semi-solid material.
It's semi-solid, yes. Wastewater, it's semi-solid, right? So you have both suspended solid, you both have soluble organics in there. But when you have high solid, we try to maintain solid content higher than 15%. It can be up to 30%. Some commercial process they claim that they can handle up to 40%, but more or less it's about around 25%. Okay, most of the facilities high solid anaerobic digestion they operate at 25%. And solid removal efficiency, wet type anaerobic digestion it's higher, 50 to 70%. But in high solid anaerobic digestion it's mostly less than 40%. And why is that? Because high solid anaerobic digestion they handle more heterogeneous feedstock, right? So that's why obviously the efficiency of solid removal going to be little bit less than wet type anaerobic digestion. Wet type anaerobic digestion is operated in continuous or semi-continuous mode, but on the other hand high solid anaerobic digestion most of the time like it's actually operated in batch mode or fed batch mode. And wet type anaerobic digestion you can provide continuous mixing, but high solid anaerobic digestion you cannot mix actually, honestly speaking, completely. It's kind of very, there are some commercial design where you can provide mixing, but the common technique is actually you have a solid tank where you actually load all the solid material, okay, and then you have liquid inoculum and you recirculate between two tanks and provide some sort of like passive mixing in the process, okay, high solid anaerobic digestion. So not totally mixed, but you can provide leachate and biogas recirculation. And wet type anaerobic digestion you have less amount of solid content and very high amount of water, okay. So typically the footprint of wet type anaerobic digestion process is much bigger, so you actually have large system, and mostly because in your feedstock you mostly have water, right. But on the other hand the benefit of high solid anaerobic digestion is you are actually dealing with high solid content feedstock, so and less amount of water, so footprint is lower than wet type anaerobic digestion process. So obviously when footprint is low your heating cost also going to be low, right. So you have a, instead compared to large tank, if you have a smaller tank, smaller footprint, so smaller you know like a lower heating cost for digester heating. Wet type anaerobic digestion it can work for only specific feedstock, it can work for wastewater sludge, it can work for food waste, but food waste if you want to go for wet type anaerobic digestion process you have to do some you know pre-treatment like grinding and make sure that it's kind of slurry, and then you can actually feed it to the digester. But high solid anaerobic digestion it can literally handle anything, it can handle like you know yard waste, it can handle food waste, it can handle any kind of lignocellulosic biomass, okay, and if there are some little bit of contamination it doesn't actually affect that much. So the process is more resilient to you know like heterogeneity in the feedstock. So typical feedstock for wet type is municipal sludge and food waste, but food waste need to be treated. High solid anaerobic digestion you can use food waste, garden waste, any kind of high solid waste, and including lignocellulosic biomass, okay. For wet type anaerobic digestion, after the digestion process is done, the digested it still contains lot of water, right. So you cannot actually directly use it as a fertilizer, you have to dewater, you have to do the solid liquid separation. But high solid whatever coming out, okay, it's mostly solid, right, with let's say 60 to 70% moisture content. Still you don't need to do any like dewatering process, you can maybe you know do further composting if pathogen content is high and directly apply to the land. So high solid anaerobic digestion, one of the benefit is less water, less capacity required. So we need smaller reactor, less heating cost, and it can handle different types of feedstock, okay. So benefit is small footprint, lower heating cost, very resilient system. So if you have some impurities like sand, fiber, any large particle, you can still actually use them as a feedstock without any pre-treatment process. And you need less critical process equipment, like you know you don't have any mixing, right. So you don't need to run any pump or motors 24/7, okay. Less maintenance in the system, but still the system needs actually like special you know like feature for or special equipment for loading and unloading, okay. So typically it's a batch process, you have a bioreactor, you open the bioreactor, you load the feedstock, you leave it for certain residence time, and after the process is done you open the reactor. But before you open the reactor it's actually kind of very critical, because you still might have some gas, methane gas, which is flammable, right. There could be some toxic gas like hydrogen sulfide. So that's why before you open the digester, after the digestion process is done, you have to actually parse the digester with some nitrogen gas, or to make sure that you don't have any toxic gas, okay, inside. Then otherwise it's going to be hazardous for the operator. So that's why, and you need some special equipment because you are dealing with very heterogeneous feedstock. So you need some process equipment to load and unload the digester, so which still gonna be little bit expensive. And another challenge is the process produce biogas, okay, but it's a discontinuous process. It's like microbial growth curve. Initially biogas production gonna be low, okay, and then biogas production gonna increase. It's gonna be stable for some time, and then it's gonna decrease. So that means your daily gas production is not same, right? So if I wanna use it for heat or electricity or something, I need, because if I produce electricity, I cannot store electricity, right? So one day you might have some surplus, and one day you may not have enough electricity. So you have to deal with the discontinuous biogas production. So sometimes some facility, what they do, they have some like big biogas bag, okay, so they store the gas, and then they actually utilize them on a discontinuous basis, okay. And in many cases lower methane yield compared to wet type anaerobic digestion, and mass transfer limitation, it's a major challenge, okay, and you are dealing with very big particle size of feedstock. It's not homogeneous. So that means always gas production, okay, gonna be lower compared to wet type anaerobic digestion. But I still feel that comparing wet and high solid anaerobic digestion, it's like comparing orange with apple, right? Because they are two different types of, and they can deal with two different types of feedstock. So we should not actually compare them side by side. And potential reason for low biogas production and instability in the process is recalcitrance of lignocellulosic biomass. Because lignocellulosic biomass or yard waste, you have something called lignin, right? So if there is high lignin content, it's kind of inhibitory to microbes. So that's why sometimes degradation efficiency is not that good. Slow methanogenesis kinetics, it's like a common problem for both wet type and high solid anaerobic digestion, because methanogen, they are slow growing microbes. Mass transfer limitation, because we don't have active mixing in the process. So mass transfer limitation is always there. One of the common approaches, we can actually have a leached tank, okay, where we can have liquid inoculum and we can recirculate, okay. That can actually help us to overcome the mass transfer limitation to some extent. Acidification of digester at high organic loading rate. So in high solid anaerobic digestion, we are dealing with solid organic waste, right? So it's much more concentrated. So that means they are going to be high organic loading rate in the process, and high organic loading rate, we know that actually acidification could be a problem. Ammonia inhibition, again, it's more concentrated, okay. So like wastewater sludge, how much ammonia you can have? Wastewater, its ammonia content is 50 milligram per liter, but in solid waste it might be few thousand milligram per liter, right? So and a high ammonia content can inhibit microbial activity. And again, nutrient imbalance could be a problem. Sometimes we may actually ignore the significance of carbon to nitrogen ratio, right? So, and it's hard to balance actually, right? Because every day the wastewater, solid waste is coming from different places. They can have different characteristics, right? So, and different carbon to nitrogen ratios. So, which can actually also create some imbalance in the process. So, any questions so far? Sorry, what? This one? This one? Okay. Sorry, what? Oh, sorry. This one, yeah.
So volatile fatty acids are produced. Thereafter osteogenesis, there any possibility of converting that network to form only hydrogen carbon dioxide by making use of any certain bacteria or something like that?
Yes.
That is so, hydrogen will be the good fuel.
That's actually a very good actually question. So yes, actually some processes are using that approach. Okay.
Maybe,
So this is called dark biohydrogen fermentation. Okay. So what we do in this kind of process, we kill the methanogen intentionally. There are some approach actually you can kill the methanogen. So you actually end the reaction here. So what you get in gas phase, you get hydrogen and carbon dioxide. In liquid phase, you mainly get volatile fatty acid. Okay. And some plant actually so previously there were a lot of research on two-stage anaerobic digestion. So first stage you produce hydrogen and VFS, and second stage you take the liquid and you kind of VFA further actually treated with anaerobic digestion process. Yes, you can produce biohydrogen as well.
methane is a greenhouse gas and it's toxic to environment also.
Sorry?
Methane is a greenhouse gas.
But you are actually combusting, you are producing heat and electricity.
Upon combustion again it produces
Producing carbon dioxide, which is kind of less dangerous.
We are losing some energy also.
Yeah, but even you are going to produce hydrogen plus carbon dioxide, so you have to deal with the hydrogen. Yes, when you actually combust hydrogen, it's going to be mainly water, right? So no carbon dioxide, but still that if you go with dark fermentation process for biohydrogen, you're still going to have carbon dioxide that you have to deal with. Okay. But why biohydrogen actually dark biohydrogen production? Because we know that there is a lot of discussion about hydrogen economy these days, right? In many countries they want to actually build infrastructure on hydrogen, okay, as a cleaner fuel. But the major challenge with dark biohydrogen fermentation is the yield is very low. Okay, yield is very low. So we cannot get more than 2 mole per mole glucose or hexose. Okay, so which is, if you see chemical reaction from 1 mole of glucose, I think we can get up to 12 mole of hydrogen, but dark fermentation process you can get only 2 mole, right? So that means yield is very low and process actually has lot of challenges still. So that's why it's still in research phase, not commercially actually implemented. So there are many commercial high solid anaerobic digestion process available in the market. Okay, so and majority of them they actually developed in Europe, and I think as I was mentioning, Europe they are much more advanced, okay, in this field, because they did not have any choice, right? Because they did not have enough space to build landfill, so they had to actually develop something that can actually help them to address their waste management challenges. So that's why there have been many commercial high solid anaerobic digestion processes, and majority have been developed in Europe. So and you are going to see they have some similarities. So for example, Drenco process, its residence time is 14 to 20 days, Compo gas 15 to 29, garage type 28 to 35, Biofarm 28 days, Biocell 21 days, CBAC 25 to 30. So more or less on average residence time for high solid anaerobic digestion process is close to 4 weeks to 1 month. Okay, so 25 days to 30 days. Okay, this is in most of the facilities they are actually kind of like mesophilic, I would say 35 and 55, 50 to 58, 50 to 55 to 60. This is it doesn't say anything, but it can be either mesophilic or thermophilic, but again I would say mesophilic is, I think majority of the AD facilities worldwide they go for mesophilic, because thermophilic they have more disturbance problem. So high solid anaerobic digestion, okay, the facility, some of the and most of there are some common feature of each commercial processes, okay, and some of the facility it's gonna look like garage or storage facility, okay. So you have a like box type reactor, okay, with some door, gas tight door. You basically open the door, okay, load the feedstock and then close it, okay, and leave it for about 28 to 30 days, and after the process is done you take them out, okay. So this is a common process, but again if you don't have any mixing, there are going to be significant mass transfer limitation in the process. So that's why most of the facilities or commercial design, they include a secondary tank, sometimes we call it leachate tank or percolate tank, okay, where we have some liquid, okay. Sometimes leachate can be collected from here, or sometimes some facility they add liquid inoculum, okay. So liquid inoculum, and they kind of intermittently they recirculate that inoculum between two tanks. So that kind of provide some sort of like passive mixing in the process. So you can overcome mass transfer limitation in the process. So organic fraction of municipal solid waste is kind of this is sometimes called box type or garage type design. So I think like here you see garage type, okay, they call it garage type design. So you have a gas tight door and you collect the leachate and you recycle it back, and a kind of you can have a sprinkler at the roof of the tank, and then you can actually kind of distribute the leachate, and so that's going to actually provide some mixing, and you can collect biogas from the top. And there are at least two commercial design that is actually based on this concept. One is smart farm, one is biofarm, okay. I think both of them are either developed in Germany or Netherlands, I can't recall exactly, okay. So this is an interior of the tank, and you can see, I'm not sure whether you can see it properly, but there are some pipe installed at the roof of the tank, okay, and they are actually doing some wet commissioning using water, okay. And this is how it's going to look like after you load the digester, okay. But obviously this was in the beginning of start. You cannot, during anaerobic digestion process, you cannot open and take picture, right? It's during the loading process. And I put actually YouTube video link, okay. So most of the commercial those vendor, they have some nice videos on YouTube, okay. So you can go and actually check, okay. I provided the link for every design, but we are not going to actually watch video on in the class, but I think you can maybe tonight when you have the lecture note available, you can go and check online those videos. But in addition to box type design, there could be other design, okay. So one process called Drenko process, if I am correct, that process was actually developed in Japan, but I might be incorrect as well, so please check, search online, but I'm pretty sure it was in developed in Japan. So that is kind of semi-continuous process. So that's a silo type reactor, very tall reactor, okay, and you are pumping your feedstock from the bottom, but they are actually entering to the digester from the top. So there is actually pipe, you are injecting from the or pumping from the bottom, but actually it's entering to the reactor from top, and when it's kind of going down, the reaction, they have interaction with microbes and organics, and it's kind of degrading, and they have a large gas holder where they actually collect the biogas, and like feedstock is added in the system, but a part of digested is actually kind of added to the fresh feedstock. So because you have to make sure that you also providing inoculum, right. So most of those design in high solid system, after the batch is done, you actually recycle a portion of the digested is in inoculum, okay. Otherwise, like if you just start with feedstock, you have food, but you don't have enough microbes, right. So you need both microbes and feedstock. So that's why most of the time digested, a portion of digested is recycled back to the process. So it's a silo shaped reactor, and limited amount of fresh feedstock is added to the digested, okay. And technology operate, they claim that this process can handle up to 40% solid, okay, up to 40% solid. there is another design which is actually a plug flow type reactor. Okay, so you are basically you have a plug flow type long reactor. Okay, and then actually they have an internal mixer here, as you can see here. That mixer, it's kind of continuously rotating to provide mixing in the feedstock, and there is some head space in the pipe or inside the plug flow type reactor. So in head space biogas is accumulated and it's collected. So solid waste is entering the system from one end, and you have continuous mixing and reaction happening, and when it's actually leaving from the other end, you have digested. Okay, so this is another design, and this is called compo gas technology, and they claim that they can handle from 23 to up to 30% of solid, okay, in their process. So yeah, there are many commercial design. So now we understand now, okay, there are two types of anaerobic digestion process. Okay, one could be wet type, one could be high solid, but for high solid it's more appropriate for solid organic waste. Okay, and there are many design available, but most of the design you know, like you can have I would say the common design is you have a digester tank and you have a like separate leachate or percolate tank, because I think North America several facilities they are actually using this design nowadays. But you can have other design like Dranco process or compo gas process like plug flow or silo type reactor as well. But let's say you are working in a consulting company or you are working in a municipality. Okay, so to see the feasibility of the process, okay, let's say someone come to you, okay, and say, okay, you know what, I have that feedstock, okay, whether I can you suggest me, let's say you are an expert, someone come to you and ask you, okay, you know what, can you tell me whether, you know, like if I actually treat this waste in anaerobic digestion facility, how much biogas that I can generate, because biogas it's ultimately your you know, way of generating revenue from the process, right? So how we can do that? Any thought? Yeah, exactly. It depends, but sometimes the poultry waste may have high ammonia, right? But what you are going to do if someone come to you and ask you, okay, you know what, like how much methane I can generate? So there are different approach, okay, to estimate how much, what is the methane potential in a feedstock, okay? Yeah, what is the methane generation potential? Sometimes we call biochemical methane potential of a feedstock, okay? So this is a term that is actually widely used to see, like, you know, if we use a feedstock for anaerobic digestion process, how much methane we can get. Okay, so sometimes we can actually do theoretical calculation, sometimes we can actually do some lab scale experiment, but theoretical calculation gonna give you maximum number, right, like theoretical number, but when you are gonna run like real process, maybe you can recover 50% or 40%, right? So there are some approaches that we can use for theoretical calculation, and that's actually sometimes very useful, especially when you are in consulting and when you want to actually make some decision without building the, like, you know, we cannot just build the facility and see whether it works or not, right? So first we have to start with this. So if we consider food waste we have carbohydrate, protein and lipid, right? And carbohydrate, protein, lipid, each component they have different methane potential. So for example, if you see carbohydrate, per kilogram of carbohydrate as volatile solid. So anyone familiar with the term volatile solid?
Yes.
So what is volatile solid? Yeah, so basically it's organic. Basically it's all. So we learned about, you know, in day one we learned about the term called volatile suspended solid. right? VSS. So to do VSS, we filtered the sample, but this is called volatile suspended solid. But here we use the term for solid waste, we use the term called VS, volatile solid. Why? Because solid waste we cannot filter, right? So that's why we call it, instead of volatile suspended solid, we call it volatile solid. That an indication, okay, how much organic is there, okay, and the method is same. You can also do total solid. So instead of TSS, we use the term TS, and instead of VSS, we use the term VS. So what is total solid? The same method. You can get a certain amount of sample, put it in oven at 100 degrees Celsius and leave it for an hour, and then after you come back, your like moisture is gone, right? Yeah, exactly. So moisture is gone. So what you have is basically total solid, right? But now if you keep that sample at 550 degrees Celsius, okay, then you are gonna get rid of all the organics at 550 degrees Celsius. Then what's gonna be left? It's gonna be ash, right? Or fixed suspended solid or fixed solid. So at 105 degrees Celsius, after you take out, you are gonna have TS. At 550 degrees Celsius, what you are gonna have left, it's fixed solid. So from the difference TS minus FS, I can get VS, right? And VS is basically my organic. Okay. So in food waste, organic can be in the either carbohydrate, could be protein, could be lipid, okay, and different component have different methane potential. And as you can see here, for carbohydrate, your methane potential is 0.415 meter cube per kilogram of VS. For protein, it's 0.496 meter cube per kilogram of VS. Lipid, 1.014 meter cube per kilogram of VS. Okay. So if we know the carbohydrate, protein and lipid content in our feedstock, we can measure the what is theoretical potential. Okay. But definitely the theoretical value not gonna, like we cannot achieve theoretical value. For example, here you can see for which compound actually methane potential is high here, lipid, but lipid is very difficult to degrade. Yeah, even if you have high lipid content, it's can, those long chain fatty acid can completely inhibit the methanogen. Okay, so but at least it can give us some indication, okay, how much methane can be generated theoretically. So let's see an example. Calculate maximum methane potential of food waste based on the following composition. So we have 88% volatile solid, 88% of solid is organic, carbohydrate is 47.3% of VS, protein 29.5% of VS, lipid is 15.5% of VS. So we can start with a basis. We have 1 kilogram of food waste. So that means in 1 kilogram we are going to have 0.88 kilogram of volatile solid, right? Our volatile solid is 88%. So 1 kilogram we are going to have 880 gram of volatile organics. So now I know the composition of carbohydrate, protein and lipid. I can multiply by those percentage and I can know in 1 gram how much carbohydrate, how much protein and how much lipid I have, right? So now I have that table, okay, where I have that yield, theoretical yield. So I can multiply by that theoretical yield and I can get from carbohydrate how much methane I am going to get, from protein how much methane I am going to get, and from lipid how much methane I am going to be getting. And so this is going to be, so 1 kilogram of food waste can give you up to 450 or 445 liter of methane, okay. But again we have to keep that in mind that it's a theoretical calculation. In practically maybe we are going to get 40 to 80, like 80% could be highest, okay. Sometimes like it could be, it depends on not just the characteristics of your feedstock, it's also depend on the operating condition of your digester, right? But that can give you some idea, okay? So if you know, if someone come to you with food waste, you can simply try to see, okay, what is the carbohydrate, protein and lipid content, okay? And you can do some rough estimation, and you can actually tell your client, okay, this is the theoretical, maybe we can recover 50%, okay, in the process. So you can even estimate biogas, there are some biogas market price, and you can see what would be the approximate revenue generation from the process, right? That can actually help you to decide whether a biogas project gonna be economically feasible or not. So another thing, so here we talked about food waste, but how about wastewater? Let's say we have black water. We want to see how much waste methane can be generated from black water. For wastewater, we use COD, right? Instead of like solid content or VS, we go with COD. So how much methane can be generated, okay, if we degrade 1 gram of COD in an anaerobic digestion process? So we can also do a theoretical. So let's say some company, industry come to you and say, okay, you know what, we have a very concentrated industrial wastewater that we generate, okay, and this is our COD, which is very high. We are thinking about some anaerobic treatment. Can you tell us, okay, how much methane we can generate? So you can simply ask them, okay, what is the COD of your sample, okay, and based on that you can come up with some theoretical calculation, and then you can say, okay, you know what, like if the process efficiency is 50% COD removal efficiency, then we might actually get that amount of methane from the process. So how we can actually calculate them? So COD, what is COD? Chemical oxygen demand, like how much oxygen that you need to oxidize some organic compound to carbon dioxide and water, right? So here, so methane, if I completely oxidize to carbon dioxide and water, I need for 1 mole of methane, I need 2 mole of oxygen, right? So 64 gram of oxygen is needed for 1 mole of methane, right? So 2 multiplied by 32, 64 gram of oxygen, or oxygen is our COD, right? So 64 gram of oxygen is needed for 1 mole of methane. So that means 64 gram of COD gonna give you 1 mole of methane. And in our high school, we learned that actually at STP, 1 mole of gas gonna occupy 22.4 liter, right? At STP, yeah. So 22.4 liter. So 1 mole gas gonna be 22.4 liter. So now I can write 64 gram of COD gonna give me 22.4 liter of methane at STP. So 22.4 liter, so divide by 60. So per gram of COD gonna give me 0.35 liter of methane at STP. But maybe you can ask your client, okay, whether you are thinking about mesophilic digestion or thermophilic digestion, right? So this number we are getting is for STP, but at high temperature volume gonna be little bit higher, right? So we can do the correction for temperature. If I am running it for 35 degrees Celsius, I can do the correction for temperature. So at STP it's gonna be 0.35 liter, but at 35 degrees Celsius it's gonna be 0.395 liter, little bit higher, right? So and then we can tell, okay, you know what, like with typically 50% efficiency, we can get what, about 200 liter per kilogram of or 0.2 liter per gram of COD, okay? So that's actually another approach that we can use. But for solid waste, it's hard to measure COD, right? Because it's a like very heterogeneous mix. So COD measurement is very challenging. So for solid waste, what we can do, okay, we can calculate methane yield from elemental analysis or ultimate analysis, okay. So how we can do that? So if we do the elemental analysis for a feedstock, okay, there is an actually device called CHNSO analyzer, okay, that can actually you can actually prepare your solid waste feedstock as a powder, okay, possibly as a powder, and that actually machine can measure the carbon, hydrogen, oxygen, nitrogen and sulfur and ash content, okay, in your sample. And if you know the elemental composition of your sample, you can actually develop a chemical formula for that waste, okay. And then when you know the chemical formula, we can use this reaction stoichiometry, okay, to calculate what would be the methane potential. So organic compound, they are composed of carbon, hydrogen, oxygen, nitrogen, sulfur, okay, and during anaerobic digestion process they are going to be converted to methane, carbon dioxide, ammonia, hydrogen sulfide. So if we can establish a chemical formula for our solid waste, I can calculate how much methane I can get theoretically, right? So how, now the question is how to establish chemical formula. So we can do elemental analysis using CHNSO elemental analyzer, okay, and then we can establish a chemical formula. And typical elemental analysis or ultimate analysis, this is actually the composition for food waste and yard waste typically. But obviously if you have a sample and if you are working with your client, you have to get the sample, you have to do the elemental analysis for your sample, okay. This is kind of typical. For food waste, for example, you have 48% carbon, 6.4% hydrogen, 37.6% oxygen, 2.6% nitrogen, 0.4% sulfur and ash 5%. So inert material is 5%. Yard waste, it's like more or less the same, okay. So we are gonna do an example, okay. We are gonna use this elemental analysis, okay, data, and we are gonna try to establish a chemical formula for a feedstock, okay, and we are gonna try to estimate what would be the methane potential for a sample. So let's see an example. A pilot scale high solid anaerobic digestion facility has an annual processing capacity of 100 tons of feedstock, okay, on dry basis. Facility primarily process 70% food waste and 30% yard waste. So whatever coming to the facility, they have 70% food waste and 30% yard waste, okay. And assume that 60% of the feedstock actually undergoes biodegradation and can be converted to biogas, right? And the process operates under mesophilic temperature at 35 degrees Celsius. We want to calculate the annual methane production. So annually, so how much methane we can get from the process, and this is the ultimate analysis data that I got from previous here, okay. So I am going to use that data and I am going to consider in my feedstock I have 70% food waste and 30% yard waste. If I mix them together, what would be the chemical formula, and then I will go to this reaction and I will try to calculate what would be my theoretical, and that's actually very handy tool. It's like really widely used, not necessarily just for research, even in industry we actually use that approach. So first thing, I have this table and I can start with a basis. Let's say I have 100 gram of waste, okay. If I have 100 gram of waste, I am going to have 70 gram of food waste and 30 gram of yard waste, right. So 70% is food waste, 30% is yard waste. So now I know that out of that 70%, 48% is my carbon, right. So I multiply by 0.48, and so that means in my 70 gram food waste I have 3.6 gram of carbon. Now, oh sorry, not 3.6, 33.6, okay. So number actually, so 33.6 gram of carbon. hydrogen I have 6.4%. So 70 multiplied by 0.064. So 4.48 gram I have hydrogen. Okay. So I can do the same for each component, right? I can do this. So for example, if I want to do sulfur, it's 0.4. So I'm going to have 70 multiplied by 0.4 divided by 100. So 70 multiplied by 0.004. So I have 0.28 gram of sulfur. But so we can, it's like simple math, right? I can use the ultimate analysis data and I can calculate how much carbon I have, how much oxygen I have, how much hydrogen I have, how much nitrogen I have, how much sulfur I have. But why I excluded ash?
Because it has no energy when
Doesn't participate in the reaction.
Huh?
Doesn't participate in the reaction.
Yeah, it's inorganic, right? So it doesn't matter whether we include or because ash is, it's not going to contribute, right? We are actually trying to establish a chemical formula for the organic part. So that's why ash is always excluded from the process. So now you can see in total, if I have 100 gram of feedstock, I have 47.94 gram of carbon, 6.28 gram of hydrogen, 37.72 gram of oxygen, 2.84 gram of nitrogen and 0.37 gram of sulfur. So let's summarize them in another table. So I have, this is what I have, right, from the ultimate analysis. Now this is in gram. So now if I divide those number gram by molecular weight, which is gram per mole, okay, what I am going to get? Number of mole I have. So for carbon it's 12, hydrogen is 1, it's hydrogen 1.007, but you know, like when we calculate we try to like round the number, so I am just using 1. Oxygen 16, nitrogen 14, sulfur 32. So if I divide them by the molecular weight, I can get number of mole, right? So 3.995 carbon, hydrogen 6.28, oxygen 2.3575, sulfur you can see very low. You can still write a chemical formula from that, but it's, we don't like a lot of fraction, right? So what we can do, we can normalize. We can divide all number by the smallest number, which is the mole of sulfur. So if I divide all number by the smallest number, so sulfur gonna be 1, and then I can get carbon gonna be 346, hydrogen 543, oxygen 204, nitrogen 18. So I can get a chemical formula which is carbon 346, hydrogen 543, oxygen 204, nitrogen 18 and sulfur. So this is my chemical formula that I get from elemental analysis. Okay. So now I am actually ready to use this equation, okay, or chemical reaction, right? So this is my organic compound. So I have value for A, B, C, D, E. E is 0 because sulfur just 1. Sorry? Oh, okay, E should be 1. Yeah, because sometimes we exclude the sulfur. Okay, yeah, I can correct that. But anyway, so 1 mole of this compound, okay, 1 mole of this compound gonna give me this amount of, it's gonna be actually 1, not 1 actually, it's gonna be 1 divided by 4, so minus 0.25, right? So again, it's not gonna change the final number that significantly, but 1 mole of this organic compound gonna give me that amount, that mole of methane, right? So I can calculate the molecular weight of this compound, which is 8243 gram of this compound per mole, right? So I know I have 346, I can multiply by 12, 543 multiply by 1, oxygen 204 multiply by 16, nitrogen 18 multiply by 14, right? So this is going to be my molecular weight, and I am going to get 183.125 mole of methane. Now the facility is treating 100 ton of waste and 60% can be degraded in the process. So 100 ton, when we actually convert to gram, it's 10 to the power 8 gram, right? And 60% can be degraded in the process. So multiply by 0.6. So this amount of this organic compound gonna give me that mole of methane, right? So now that mole of methane, so now again we know that for 1 mole at STP it's going to be 22.4 liter. So I can multiply by 22.4. So this is going to be the amount that I have at STP, and then but I'm going to be running the facility at mesophilic temperature at 35 degrees Celsius, right? So now we have to do the temperature correction, and then this is going to be my final number that I am going to get. Okay. So if we can do the elemental analysis for a solid waste, we can establish a chemical formula, and we can use that chemical formula to calculate theoretical methane potential for a sample. But again, this is a theoretical number, right? But in reality, maybe you are gonna, this is not theoretical because you already considered that 60% gonna be degraded, right? So it's not maximum methane potential. So any questions so far? I'll correct that part, and I'll so before I share the thing, like I can actually like correct that number there. Actually, there is another chemical, another reaction that is excluding sulfur, because sometimes sulfur content, if it's really low, you can actually ignore the sulfur part. Okay. Any questions so far? We're good. Okay. So now we learned 3 theoretical approach. Okay. So first one is, if we know the protein, lipid and carbohydrate content, we can estimate what is the methane potential. If we are dealing with wastewater, if we know the COD of the sample, we can estimate. Huh?
COD or BOD?
COD, because this so this is actually COD. But again, like BOD means, it's biodegradable. So if you use BOD, that is kind of like, gonna give you what you can get practically. But COD is more handy too, actually. It's easy to analyze. Within 2 hours, you can get some number, right? And again, you can decide, okay, or you can just make some assumption, 50% gonna be BOD. Okay, or if you know the COD to BOD ratio. So again, you can do, because as long as we know the relationship between our COD and BOD, they can be actually used interchangeably, right? So far we learned 3 approach. From protein, lipid, carbohydrate content, which can be handy for food waste. We learned for wastewater, if we know the COD, we can do some calculation. For solid waste, if we know the elemental analysis, okay, carbon, hydrogen, oxygen, nitrogen and sulfur content, we can estimate methane content by establishing a chemical formula. But how we can do that experimentally in the lab? Sometimes you may want to further validate it using, kind of some sort of lab experiment, right? Especially when you are doing some research. So we can do that using a technique called biochemical methane potential test, or BMP test. Yeah, BMP test. So how we can evaluate the methane potential of any waste or wastewater, high strength wastewater, experimentally. So we can use a test called biochemical methane potential test. It's a very handy test, simple batch test, not very expensive, and required 1 to 2 months, mostly 1 month. Okay. So, and this is a typical setup. Okay, but there are some advanced actually device available in market, like commercial device. So when you do this kind of bioassay test, every day you have to go to the lab, you have to take biogas sample, do GC analysis to see methane content. Okay, you have to measure the volume of biogas produced. Okay, but there are some device in market right now. They can directly actually measure the methane volume. Okay, and the data can be recorded using software in the computer. So after you start the experiment, you don't need to even go to the lab. After the process is done, you can just get the data from the computer. But yeah, like last I think 10 years, this kind of equipment became very popular. But I remember when back in 2008 or 9, when I was running this kind of experiment, sometimes I had to stay overnight in the lab, because let's say I'm running 60 bottle. So for 60 times I have to take sample, go to the GC and do the analysis. But nowadays it's very convenient that, you know, like computer can record the data. And it's not rocket science. What happened, like, you know, biogas, you have carbon dioxide and methane, right? And you can have some sulfide. So if you pass that gas to some alkaline solution, okay, it can actually absorb all the acidic gases. So in the gas meter, whatever gas is going, actually it's mostly methane, right? So yeah, so this is kind of like a, but still they are charging, like this setup, this is actually from my lab. Okay, so this setup, I think we buy them about $10,000, okay, each setup for 6 bottle, or you know, sometimes we can run more. But this setup, I think it's right now market price is around $35,000 to $40,000. Okay, and it's not a rocket science, but still it's quite expensive device. Okay, but it's very popular to industry, because industry, you know, like when they run experiment, they don't want to actually spend a lot of time actually working in the lab, or, you know, like it's kind of very handy tool for them. So yeah, so now biochemical methane potential test. If you have a feedstock like either waste or wastewater sample, so first we have to characterize the feedstock. Okay, and for this kind of thing we typically go with COD measurement. Okay, and then we have to bring some seed or inoculum. So seed or inoculum, we can, if we have a, let's say, large scale AD facility in your city, you can go to them and you can ask them to give you some digestate, because digestate that is coming from full scale digester, they are already enriched with different types of anaerobic microorganisms, right? So you can get those kind of culture and use them as a seed or inoculum for BMP test. And for inoculum, we typically do VSS or VS. Okay, so sometimes if it's kind of slurry, you can go with VSS. If it's like solid, you can go with VS. So there is no strict rule for that. And then we have to design some bioassay, okay, or design some BMP test based on food to microorganism ratio. So what is food to microorganism ratio? We learned that yesterday. It's a balance between substrate and microbes, right? So that means, and we know that actually high food to microorganism ratio, it's not good. So that means you are actually giving more food than they actually can consume, right? So that's why there is a recommended range for food to microorganism ratio, and you should not go beyond that. And then after you start your experiment, you have to collect the methane production data and you have to do the data analysis. So typically BMP test, its food to microorganism ratio, it's range from 0.25 to 5 gram COD per gram VS. So COD is for substrate or waste and VS is for inoculum or seed. So based on food to microorganism ratio, so most of the time, like if you don't know what would be the optimum food to microorganism ratio for your feedstock, like it's better to go with low FM ratio. So most of the time, if we don't know, like, you know, what would be the optimum, we go with 1. Sometimes we try multiple food to microorganism ratio, but if we don't want to do a lot of experiment, we end up with doing, if I need to pick one food to microorganism ratio, I will go with 1. Okay. So, FM ratio here you can see it's like almost similar equation that we learned yesterday. So, FM ratio is gram of COD of substrate and M is gram of VSS or BS, whatever you use, of inoculum. And so, basically it is volume multiplied by concentration, right. So, if a mass of food divide by mass of microorganisms.
So here VSS of inoculum is just like ml/VSS, just like VSS of inoculum.
Yeah, microorganisms, yes.
So it is just like ml/VSS of wastewater.
It's you can say MLVSS. I won't say, yeah, like it's MLVSS term is more used for activated sludge process, but here I would say VSS, okay, or sometimes you can do VS. Sometimes actually, like like digested solid content could be high and filtering may take really long time. So sometimes actually researcher they prefer VS instead of VSS. So now if you have a reactor or bioassay, okay, bioreactor, you are going to know what would be the working volume that you are going to be dealing with, right. So typically those bioreactor they are from 300 ml to 1 liter, okay. So we need to know if we have a certain working volume. So this is going to be, let's say if I need to know how much substrate I am going to add and how much inoculum I have to add to achieve certain food to microorganism ratio. I think someone has some question. So did you have a question? You had a question? Okay. Yeah. So now you can see I have two equation. So first I have to decide what food to microorganism ratio I am going to use. I have to measure that COD of my sample. I have to measure VS or VSS of my inoculum, and I am going to know what would be the working volume of my bioreactor. So if I know them, I have two equation and I can see I have two variable, unknown variable V1 and V2. I can actually estimate them V1, V2. So after I decide, okay, or estimate what is the volume of food waste or sample that I need and what is the volume of inoculum or and seed that I need, I can actually start my experiment, right. So first we are going to add volume of estimated seed and substrate in my BMP bottle, and then check the pH. So we have to make sure that when we start there is enough alkalinity in the reactor, okay. If there is not enough alkalinity, we have to add buffer and we have to actually adjust the pH to close to 7 or neutral pH. And then the step is we have to purge the reactor with nitrogen because it's an anaerobic process. So we have to make sure that there is no dissolved oxygen in there. And then after purging with nitrogen, we can close the reactor and we can put it in the incubator, and over time we can measure the gas volume and methane composition. But at the same time, okay, we have to run a blank test. So what is blank test? So blank test, we are going to have similar, like reactor, but for one reactor, the feedstock or substrate going to be replaced with DI water. And why is that? Because when you have like an incubation, like during incubation, you expect that gas is going to be produced from your substrate, but there are some organics in your seed or inoculum itself, right? So how do you know that there is no gas production from inoculum itself, right?
So it is just to subtract.
Yeah, so that's why
When we're going for absorption spectroscopy, then we do blank test.
absorption spectroscopy for what? So here we want to know, okay, what would be the biogas production from seed or inoculum itself. So that's why we ran a same test, but without any substrate, and we replace the substrate volume with DI water where there is no organic. So we call it blank. So if I have a test reactor, okay, test reactor I have, let's say 100 ml biogas production, and blank is showing me 10 ml. So I can assume that, okay, 10 ml, I am seeing 100 ml, but 10 ml is actually coming from inoculum, but I am interested about substrate. I am not interested about how much gas is actually coming from inoculum itself, right? So that means my true gas production gonna be 100 minus 10, 90 ml. So for that correction, we have to run some blank test, okay, and then you are gonna collect your data, and this is an example data, okay. So let's say, you know, from you are running the test for 17 days, and this is your daily gas production. So what we do, we kind of look into cumulative gas production data, okay. So cumulative gas production data, and you can see after a certain period of time it reached about 1300 on day 13, and then it kind of reached a plateau. There is not significant gas production after day 13. So if you see the graph, time versus cumulative methane production, you can see after day 13 it reached a plateau, right? So at this stage we can decide, okay, you know what, it's the experiment is done and we can stop the, you know, our test, okay. So when we should stop? When the cumulative gas production, daily gas production is kind of per day gas production is less than 1% of the total cumulative gas production, we can assume that it's kind of ready to stop. So for example, you can see here 1300, after that actually it was kind of quite stable, the gas production, right? So sorry, yeah, so now we can actually stop the, so that means there is not much biodegradable organics left in the process, so we can stop the experiment and we can start our data analysis. So now we are going to see an example with some calculation how the data analysis part is done, okay. So design a BMP test using food to microorganism ratio of 2 if the substrate and seed characteristics are given in this table. You can see you have TCOD, you have VSS, and working volume of the bioreactor is 500 ml. So my V1 plus V2 gonna be 500 ml, right? Conduct a COD balance if the final TCOD concentration is 15 gram. The experiment was conducted at 35 degrees Celsius. Total methane production was 1822 mil, and total methane production from blank was 100 mil. So my actual gas production was 1722, right? And this is my characteristics. So first I have to calculate what is should be the volume for V1 and V2, right? So and food to microorganism ratio, in the question we mentioned that it's going to be 2, and I know the COD, I know the VSS, right? So I can actually plug those number. So 2, 40 gram per liter, 10 gram per liter, and my V1 and V2. So that means V2 equal to 2 multiplied by V1, and my V1 plus V2 gonna be 500 ml. So that means if I solve that, I need substrate, I need about 167 ml, and seed or inoculum I need 333 ml. Okay. So now COD balance. So what is COD balance? COD balance is done to make sure that the data that you are getting, whether it's reliable or not. It's kind of like, you know, some sort of like, you know, quality management in your test. So for any BMP test we do, we should also do a COD balance to make sure that we don't have any experimental error, and the data that we are getting we can trust. And why? Because it's an anaerobic reactor. What if you have some leak in the reactor and some gas actually it's kind of, you know, leaked from the reactor and you could not actually collect them, right? That could happen because it's an anaerobic reactor. It's a kind of very sophisticated. So that's why COD balance, it's a common approach that is actually done to make sure that the data you are getting is reliable or not. So what is COD balance? COD balance is methane production that we are actually observing experimentally divided by methane that can be actually theoretically produced from the COD removal, because we know the initial COD that we put in the reactor, we know the final COD. Okay, so from the COD removal, because we know that per gram of COD, if we run, like from one of our previous slide, if we run our experiment at 35 degrees Celsius, per gram of COD should give me how much? Like 395 ml of methane. Okay, so now, so actual methane production was 1722, so 100 was for blank, and initial COD we know the COD for both substrate and inoculum, and we know the V1 and V2, right? So volume multiplied by concentration, we can get the mass of COD that we had in the reactor in the beginning, which was 12.34 gram of COD, and we know the final COD concentration, which was 15 gram per liter, and we know the total working volume, which was 500 ml. So that means final COD was 7.5 gram COD. So that means during this process incubation period, we remove 4.84 gram of COD. Okay, so we expect that, okay, that 4.84 gram of COD actually converted to methane, right? So we want to see whether it's kind of match with our experimental observation or not. So 4.84 gram of COD removed, and theoretical methane yield at 35 degrees Celsius from one of the previous slide, it's 395 ml methane per gram of COD. So my theoretical methane production should be 4.84 multiplied by 395. So I should see 1911 mil of methane, but experimentally I found 1722 mil of methane. So if I do use this equation, my COD balance is about 90%. So can we trust this experiment or not?
We can.
Huh?
Just we have to know that this is the correction factor.
Can we trust?
Yeah, I feel we can trust.
It's 90% close, not 100%. We can still actually trust that data. Okay, if it's like 80 to 90%, it's still acceptable, because you remember a portion of COD should go for new cell synthesis by microbes, right? So, and for anaerobic microbes, the 5 to 10% can go for new cell synthesis. So 90% is actually good enough. So if it's 90%, it's good enough. But some paper, if they actually report you, okay, they have like perfect 100%, don't trust the data. Okay, so you cannot get, yes, sometimes it could be coincidence, sometimes you could see close to 100%, but if it's 80%, still it could be reliable. Sometimes it could be 110%, so that means 10% could be some sort of measurement error, so which is still acceptable. Okay. Any questions so far? Okay, so if not, then here we stop. So here we finish our second topic on anaerobic digestion, and all actually lectures note is going to be available to you, I think tonight, and tomorrow we are going to cover so this GIAN course on conventional and emerging processes, bioprocesses for waste and wastewater treatment. So far day 1, day 2, day 3, we mostly talked about like conventional processes, activated sludge process, composting process, anaerobic digestion process. So tomorrow my lecture is mainly going to be focusing on some emerging processes in this area. Okay, so thank you so much and see you tomorrow. Okay, thank you. right? At 4 p.m. Yeah. So meanwhile you can have your lunch and you can actually interact with other faculty members. Yeah.